Oh, right. Let me check. Okay. Things seem to be in order. Hello, everyone. Welcome to the stream where we continue to make progress in exploring modern rendering in Vulkan. Last stream was yesterday, so there's going to be a stream today. We'll see how much time it will take. And then there's not going to be any streams for the rest of November. And then hopefully we'll pick things back up in December. A very brief recap about what happened yesterday. Yesterday we implemented texture loading and we implemented bindless textures, which allowed us to, wait 1 second, I'm cheating here, which allowed us to do, render the scene using our existing renderer in sort of full fidelity, you might call it this. It was painful because of some bindless stuff that I did not anticipate would be painful. But we did get there in the end. We are rendering the scene. And today the plan is to start doing ray tracing. Now, I want to do two quick things. I want to talk about one quick thing and then do one quick thing that we didn't get to yesterday, which is not super important, but my aspiration with ray tracing, there is no way that today we will be able to actually take full advantage of ray tracing capabilities. For all I know, we may hit significant issues somewhere that are going to be very difficult to debug. Debugging is going to be rough because I don't think RenderDoc has full support for ray tracing. I'm not sure. We'll find out. So maybe there'll be GPU crashes. Like, it's going to be wild today. Maybe, hopefully not, but we'll see. And so realistically, I think the absolute best that we could expect is to be able to trace a shadow ray per pixel. But even that we might not get to. So because of this, I want to be a little bit less of a rush and just accept wherever we get to. So two things. One is, yesterday I talked a little bit about descriptor buffers. I looked a little bit more at the spec yesterday, and we are not going to be using this for the exact same reasons that I said yesterday. They actually are not going to make anything simpler for us. And all of the complications that we had, or most of the complications that we had yesterday, were due to the descriptor indexing bits that are still relevant when you use descriptor buffers. So like, there is no point. It's just not worth the complexity. The other thing that I want to do, somebody asked last time on stream, and I said, yeah, it's like probably not very difficult. And then somebody asked a similar question a couple of streams ago. So I think it would be worth actually enabling alpha testing, because it's not as simple as you might think. So I want to spend a little bit of time on this, and then we'll start doing ray tracing. So I talked about buffer device address like a few years ago. There's a Niagara stream about buffer device address. I don't know. My impression is it doesn't come with a significant performance hit, but I'm not 100% confident in this. But I think we even tried, like on NVIDIA, I think we tried fetching vertex data with buffer device address and it was fine. The difficulty that we've ran into with buffer device address when we tried it, like, so there's a stream from a few years ago. I seem to remember there was a problem. Essentially, if you are not using mesh shaders, and you pack draw calls in like a single draw call like we do, then you have to use multi-draw indirect, which doesn't support buffer device address when you specify the index buffer. And so for the index buffer, you're still looking at manually managing a big chunk of memory, and so buffer device address doesn't help you. Otherwise, yeah, so I'm not aware of significant performance issues with buffer device address. I assume it's fine. For us, for now, I don't think it's like worth the extra complications, but maybe at some point we'll explore this again. I wouldn't worry about which buffers. Like, the way buffer descriptors work on most hardware is Uniform buffers are special. There's some cases where using uniform buffers is faster than storage buffers, and when you use buffer device address, you'd have more of a similar behavior to storage buffers. So if you're replacing uniforms, I would be worried, but not because of the buffer device address. If you're using storage buffers already, then using buffer device address, generally speaking, is roughly the same as what the GPU is doing already, because usually the way storage buffers work is there is a buffer address, literally like a pointer to the GPU memory, somewhere in the descriptor. And then the GPU reads it and then reads data from it. And so you can do it yourself, it's fine. So if you are already using storage buffers or some non-uniform buffers, I think it's probably fine to migrate, knowing that not all hardware supports it. Anyway, so somebody commented yesterday on plans, which are clearly not rendered correctly right now because they are using transparency and we don't support transparency. The other thing that I noticed after looking again at the scene is like, so if you look here, obviously there's plans that just look like polygons because they are, but also there's this piece of the wall that looks off. And the reason why it looks off, it's actually a decal. It's not a piece of geometry that's like separate. It's like laid over the geometry of the building. And all of these should be using alpha, and we don't have alpha support right now. Now, the reason why I wanted to talk about this is it's an interesting complication that in general people who are writing high performance renders should be aware of. So let me bitrate, it's fine. Okay, so I already did like this work kind of off stream, and I just want to very, very quickly talk about this. Maybe I'll just pull, I have like a Git stash for this. So in theory, we now have access to alpha in our shader. And in theory, we can just do this. This is like an alpha test done manually. So if the alpha is less than 0.5, we'll just discard the pixel. Let me disable vsync so that we have more accurate performance measurements. And you know, this GPU is fast, so like whatever we do can't be too slow, but. So this is the scene as we render it right now. There's issues with like plans and cards and stuff, and it runs at 0.83 milliseconds per frame. It fluctuates a little bit, but it's like 0.83. So let's say I enable this alpha testing. Watch what happens. It is now 0.94. Now you see these plants look fairly decent. These leaves look very nice. We want this change for quality of rendering, but it degrades performance visibly. So we went from 0.83 to 0.94, so it's 0.1 millisecond, but that's like more than 10% of the frame time. The reason why, and you may think, oh, maybe there's like consequences for occlusion culling or something like that. And there are some, like more correct rendering, because we're rendering a slightly different picture, right? Like it makes sense that the performance is slightly different. Let's say we do something like this. This condition never executes because alpha can never be less than minus 0.5 because it's like a value between 0 and 1. We are still at 0.93 milliseconds. So the performance penalty that we have is not because we are discarding pixels, because now we are rendering the exact same thing that we were rendering before, but now there is a discard statement in the shader that never executes. And despite the fact that it never executes, to take a substantial performance hit, like a 10% performance hit here, for doing that. So why does this? The reason why I wanted to talk about this is this can happen in renderers. I think this was a problem in Godot for some time. I forget if they fixed this. I'm sure there is like a non-zero amount of renderers that have this issue. Why does this happen? The issue is that when you think about the graphics pipeline, the way it's I will give a brief explanation because the main purpose of the stream is like ray tracing, but the reason why this happens is the way people are taught graphics pipelines in like school or whatever, to the extent that people even teach that in school, I'm not sure, is there is a depth test, and then, well, I don't know how it's taught. There is like different versions, but it's not, I think the way it's taught, it's okay. The logical version of the pipeline, let's start the other way around. So the logical version of the pipeline looks like this. I think this is probably what the official like docs for OpenGL and D3D say in Vulkan. There is a pixel shader, and then there is a depth test write unit. So you run the pixel shader, and then you look at the result, and then if the depth is less than whatever's in the buffer, you write it out. This is nice because this means that many things can happen inside the pixel shader. One thing is we can discard the pixel, in which case we shouldn't write the test. It doesn't matter if we test the depth, but we shouldn't write the depth. And then also you could write out custom depth from the pixel shader. Hardware doesn't. This is like super inefficient because this means you are shading all pixels regardless of whether they are occluded by the Z buffer. So usually what actually happens is you want an early depth test. But what the hardware actually likes to do in some cases is actually have a depth test write unit that runs before the pixel shader or after, usually not both. And when this happens, the choice to do discard, so like how does this work if you do this before the pixel shader? Well, if you have a guarantee that the pixel will be written to the screen if it passes the depth test, then you might as well update the depth value before you run the pixel shader, because it can't change it. The case when this is not true is if the pixel shader writes depth, or if the pixel shader drops the pixel, in which case the write shouldn't happen in the first place. There is more complicated versions, and if in this naive version you could imagine that using discard instead of this path, you use this path, which is much less efficient. This is not quite what happens in hardware. I don't want to go into like complete details right now, because again, it's like supposed to be a ray tracing stream. I just wanted to go over this quickly. And the way you solve this is by moving this essentially says enabling discard on every single pixel shader is like a significant issue. It's an even more significant issue on some mobile hardware, but it is still a significant issue on my AMD GPU, which is the latest AMD GPU that exists today, right? So like this is a current problem. And if you have a renderer that just has a discard in all of the pixel shaders, you're leaving performance on the table likely. There's cases where this is less true. For example, doing a depth pre-pass without discard and then doing like regular pass with discard is okay-ish. It's like less, it's usually not a problem. But because we don't have depth pre-pass and using a depth pre-pass doubles the geometry cost, this is like a current problem that we have to solve. And so the way, the reason why this is complicated in our case is we have one draw call. And so to fix this problem, we have to move this draw call we have to move the objects where this rejection of pixels matter into a separate pass using a separate shader. Let me just actually, again, because this is a ray tracing stream and because I already wrote the code, and the code is fairly simple, let me just show you what the solution can be. And then we'll pretend that I've written this code on this stream, and then we'll actually move on with ray tracing. This is complicated because we have three versions now of the pipeline. We have traditional mesh shading, traditional rasterization, and then we have mesh shading with task shaders, and then we have mesh shading without task shaders. I'm gonna remove this middle one in the future off stream probably, just cause like it's way too much stuff to deal with. But essentially what you want is you want to have, right now we have three passes. We have two passes, sorry. We have an early pass where we render objects that were visible last frame, and we have a late pass. And between this stuff, we have this occlusion pyramid that's been built, and then we use it for occlusion testing. You could solve this issue for blended objects that don't write depth. You have to move them out of the early pass anyway. I talked about this, I think, yesterday, because you can't have them write depth. So you have to move them like here, right? So you have to have a solution for moving some of the objects to the end of the frame. For alpha tested objects, you technically have two options. One is you render them at the end of the early pass and the end of the late pass, which could be valuable if you want the alpha tested objects to still contribute as occluders to the occlusion depth buffer. This could be valuable for very, very, very dense forest scenes or something like this, but it's a little bit more cumbersome because now you have to have, this special thing that's only true for the alpha tested objects, because for blended objects, you have to not have them right depth, so you have to move them out of the occlusion pass. So what I decided to do is just have this notion of there's going to be stuff that's rendered in separate passes here. And then the way I did this, the way I implemented this is inside every draw call, I have this thing called post pass, which is what's the index of the pass after the main geometry passes that we have, that this should be rendered in. And then for now, there's just one, right? But in the future, for example, we could add one more for translucent objects. Maybe we'll add one more for double-sided objects. Whenever you want a major PSO change, essentially, this is where you can do that. This is how you can do this. I very quickly wrote this code. It's not maximally efficient necessarily, but when we process GLTF content, we say, oh, everything that is not opaque should have post pass 1, which means it will be rendered in this third pass, right? And then there's some pipeline nonsense because you have to duplicate a bunch of pipeline stuff. And then whenever, where's the actual shader changes? Yeah, so whenever you do occlusion, or whenever you do visibility culling, you have to basically only render objects that you want to render right now. And then I had to do a couple small changes because of the occlusion stuff. Occlusion is fiddly, so this is why it's valuable to just forget about these objects from the occlusion writing perspective. But anyway, I think I'm just gonna commit this code as is, because it's not, the details are not super important once you understand the general paradigm, where we just now have 3 passes, where in the third pass, in the first 2 passes, we just skip some objects, and then in the third pass we don't. There's slightly more efficient ways to handle some of this stuff, but the reason why, what this allows us to do is, instead of doing the discard unconditionally or conditionally from the runtime perspective, this allows us to have a separate PSO that has the discard check, and then our main PSO doesn't. This means that we can have these objects being rendered with the discard, but only in this last pass, which means that the first 2 passes don't suffer from the efficiency perspective at all, so they don't suffer from all of these problems. But we still get the visual effect that we want, which is to discard pixels. And that's kind of it. So I quickly threw this together half an hour before the stream started. It's not it's not the most earth-shattering code, but if we run with this code, then we can see that our time is now 0.86 instead of 0.84. So there is a small performance hit. I think it's because the occlusion efficiency is a tiny bit lower. If you look at these objects, for example, I'm not sure if this is going to be visible. This is not going to be visible, but let me run this in RenderDoc. And in RenderDoc, you will now be able to see 3 passes, so we should do RenderDoc capture anyhow. Oh, and I'm going to show the debugging in RenderDoc for the stuff that we did yesterday. So if you do this capture, let's just do this in small resolution, doesn't matter. Under the RenderDoc, with this change, what you see is we actually now have 3 passes. We have the pass where we do the main sort of occlusion buffer fill with the objects that we now are known to be visible. Then we do a second pass where we actually don't render much or anything at all. And then we do a third pass where we render the objects again. There's better ways to do this. So for example, we still have a I structured things to make it much easier to just add this in, But this does mean, for example, that we have 3 render passes instead of 2 render passes. In theory, you could imagine filling 2 buffers with stuff to render, but it's just more buffers to manage, etc., etc. It's all not too bad the way it is. And what is different now is this. So in the one moment. Yeah, so you can see that at the end of the second pass, we actually don't have any vegetation rendered. Which also means that, for example, from the occlusion perspective, like, for example, maybe these objects that are behind the bushes, maybe some of them were not rendered before because they were behind this kind of dense bush. But it doesn't really change the overall triangle count much. I think it went from 1.00 million to 1.01. So I think for now it's like a pragmatic solution that is maximally quick to implement and solves our efficiency issues. And then we just render these objects in like the last pass. So if you look at the geometry that's been rendered here, it's just the vegetation plus the decals. So like this, for example, if you can see this thing, this is like a thing on the building that's like a decal. And we'll want this type of approach in the future anyway for translucency and some other stuff if we get to this. So I kind of wanted to implement this this way for now. Anyway, so that is it. That kind of concludes the stuff we did yesterday. And yeah, oh, the other thing I wanted to note is, so yesterday at the very, very end, we went through all of this trouble with like partial descriptor buffers, or I forget, like runtime sized, variable sized descriptor buffers. It's actually, I'm now happy that we've done that, because if you look in RenderDoc, this interface is a little bit confusing. I was confused by this yesterday. I think you maybe press here. Yeah, okay, you press here instead of there. Okay. So right now, if you look at RenderDoc, it actually only shows us 300 something descriptors. But this buffer is allocated, this buffer could hold more. Buffer could hold like 64K or whatever. If you do 64K, then RenderDoc will show you the entire 64K, but it will say for most of them, these are not filled, right? And so from the debugging usability perspective, it's like nicer to only allocate the descriptors that you need, because then RenderDoc knows not to display like this immensely large table of like, you know, thousands or tens of thousands or hundreds of thousands of descriptors. So that's kind of it. I think this might be our last use of RenderDoc today, because I think RenderDoc doesn't do ray tracing debugging, so we might be on our own. But yeah, I just felt this is important. These alpha issue is important to talk about, because it's a subtle thing that people don't know exists. It's a subtle gotcha. And if you do have this unconditional, if you don't have a depth prepass, or if your depth prepass uses discard, and if your discard is like in every shader, you probably have a performance problem that you should address. All right, so we will pretend that I've just written this code. This code took me like, you know, 20 minutes to write a stream of something. So we'll just pretend I've been writing this code. Separate class for alpha discard. This allows us to reject pixels in alpha discard in objects with alpha without affecting PSO for opaque objects, which would have cost us 10% of frame time on RDNA3. And this percentage could grow if we do ray tracing in the pixel shader, because the cost of doing discards unconditionally on a full scene like this, let me go back to Wayland, is it can scale with the cost of the fragment shader, and the cost of our fragment shader is relatively small now. But so now you see that, for example, this decal is like much nicer, and in general the scene looks nicer. I should say, with ray tracing, you have to go through a bunch of extra weird stuff to do alpha testing, and we will definitely not do this today. But our aspirational ambition is to do ray tracing support for geometry at some very minimal level. So that is that. Now let's talk about ray tracing. I looked a little bit yesterday at the docs. I sort of know what we need to do a little bit better now, but not, I kind of knew the high level anyway, so it's gonna be whatever essentially, I have very zero context for what's about to happen. I just opened a couple of extension pages and just glanced at the functions available and stuff like this. So we'll see what happens. But fundamentally, what do we need? What do we need to do? Like, where are we trying to go? People asked me about ray tracing years ago, and I kind of made a comment that I don't really like all of this software infrastructure is being built around the ray tracing, but I do like the hardware pieces that are responsible for it, and so I wish the hardware pieces were more directly available. I think this was before ray queries and DXR 1.1. But the way ray tracing is specified in Vulkan, there's kind of three components. There's three extensions. There is the acceleration structures, which we will start with. There is the ray tracing pipelines, and there is the ray tracing query. So the piece I don't like, the piece that I think is artificial and doesn't really actually have real hardware backing it, and the piece that we will completely ignore, pretend doesn't exist, and never touch even if we really want to, is this. Ray tracing pipelines do not exist as far as I'm concerned. The reason is the ray tracing pipeline function mostly is to do indirect shader dispatch. It's like you have this ray that hits this object has a material, that material has some shader that should be responsible for doing that processing, etc. As you probably noticed, a lot of the time that we spend on the stream is talking about sort of real hardware, and these streams talking about real hardware, how it works, and the trade-offs and stuff like this, and trying to go lower level. Like, we ripped task shaders out. The reason why, well, they're still in the code, but I'm gonna delete them today, later after the stream. The reason why we did this is not because it's a bad concept necessarily, but on AMD hardware, it corresponds to compute and it's implemented inefficiently in the driver. And so it penalizes our performance because there is an abstraction that we can't bridge other than just not using this. And I have similar feelings about ray tracing pipelines. I don't like them. I don't want to go there. Also, there's now work graphs. If you look at ray tracing pipelines and work graphs, they're kind of somewhat similar-ish. I mean, they're not similar in the details are completely different, but conceptually they kind of solve a similar problem. There is this complex dependency graph between various computational workloads. How do we execute this on the GPU? So don't want to go there. This leaves us with two components that actually are, as far as I know, we are streaming from an AMD GPU. On AMD GPU, I believe they have a lot of stuff implemented in compute except for the actual ray triangle intersector, but I'm not sure. We'll find out. On NVIDIA, I believe there is more stuff in hardware, but I don't know. NVIDIA doesn't really talk about this. But the reason why we need both is this. Fundamentally, when you do ray tracing, you have a ray and you want to intersect the ray with your scene. Your scene is complicated. We have a bunch of geometry, a bunch of objects, etc. And you don't want to just trace a ray through the scene by intersecting with every triangle on your scene, because that's too slow. So what you have to do is you have to build a tree, which is the acceleration structure, which will represent your geometry as a tree, literally, of usually bounding boxes. So it's usually called BVH, bounding volume hierarchy. Usually the volume is the bounding box. And so you have a box and it's split into two boxes, and then each box is split into two more and stuff like this. And at some point in the last box, there's a few triangles. So you trace a ray through this tree hierarchically, you reject, you go into the boxes that you intersect, and then you land in boxes with triangles, then you do intersection. Depending on your GPU, parts of this process may be hardware accelerated now, and parts might not be. My understanding is on AMD, the actual BVH traversal is compute, and the triangle intersection is hardware. We can actually look, because RAD has sources for this, which we might. But you have to build the structure, and you have to. The ray tracing abstraction only has a 2-level BVH. So there's a bottom level acceleration structure and a top level. It's hard-coded as a 2-level. It's kind of unfortunate because I think sometimes you want 3, you want like 2 top levels, but like it's fine. Hopefully it's fine, we'll see. It's definitely fine for our use cases, just that when you have dynamic scenes, etc., I'm not sure that it's the best. Having just 2 may not be the best. Having 3 I would have preferred. But the bottom level is the acceleration structure around triangles. And the top level is an acceleration structure around objects. And so what happens usually is you trace array through top level, you get the objects, and then you trace arrays through the respective bottom level structures. The reason why you want this is bottom level is around triangles, and triangles tend to be static. In our case, for example, everything is static, but we could move any object right now without any changes to anything. It's like a few bits in memory that specify the position of every draw call. And so if we wanted to do animation on objects, it's very, very simple to do. If we wanted to do animation on vertices, it's harder to do because we have meshless, we have cone culling, etc., like it gets trickier. And the ray tracing abstraction explores the exact same division where, okay, geometry tends to be more static, but where you place objects tends to be more dynamic. And so if you want to move objects, you could update classes separately from BLASes. So you move the object around, the tree around the object structures changes, but the actual objects don't. And I should say, you could have multiple classes. So for example, maybe you have a static scene class and a dynamic scene class, and a static scene never changes or changes when you stream or something, but dynamic scene changes every frame. And then there is also a concept in these trees of build versus refit. Build is when you have a bunch of data and then you build a new structure around it, right? So that's a comparatively slow process. We'll see how slow it is. But hopefully you do this fairly rarely. But then what happens is if one object changes, moves a little bit, what you could do is instead of rebuilding the whole thing, you can do a refitting process. What refitting usually means is, I don't know the details of what the drivers actually do. I don't even know. Refitting is exposed as like an update. I don't know what it does, but classically what refitting means is, let's say you have a bounding box and then you have the object inside of the bounding box. Let's say the object moved to be here in this new position. Instead of rebuilding the whole thing, you could update the bounded box upstream of the objects that moved to accommodate the new bounds. So now instead of this smaller outer box, you will have this outer box, a larger one. It's less efficient because now this box has empty space. So if you don't want to do this, you have to do like optimizations. Technically you wouldn't have empty space. Empty space is not quite the right way to classify this because in this specific case, refitting would actually be fine because there is just one object inside of this box, and so you'll just adjust the box to like be tightly fit. But if there's other objects, then sometimes it's more efficient to rebuild portions of the hierarchy. Anyway, so that's why acceleration structures are needed, and Vulkan exposes a bunch of APIs to like hide the details of how this all works from you. And it's kind of beneficial because, as I said, for example, I think on NVIDIA there is more hardware acceleration than AMD, which means that you want an abstraction that hides these details from you. How well this works, I don't know, we'll find out. And then ray query is the mechanism to actually do ray trace through this BVH, which again, you trace the trees, you trace more trees, you do triangle intersections, you get the intersection point. And ray query is different from ray pipelines in that ray query is a mechanism that's available to you in any shader stage, whereas ray pipelines are this separate world that you live in, which we will not go towards. So the plan is then to take our scene, to build acceleration structures from the scene, and then to use the ray queries in the fragment shader to trace a ray through that scene as a shadow ray, and hopefully get some shadows. Now, there's a lot of complicated stuff here when it applies even to our simple renderer, which we will ignore for now to the extent possible. For example, our scene has level of detail. This means that the same object may be instanced throughout the scene at different levels of detail, and these levels will switch when we move the camera. This means that the way you structure your, and you could build the ray tracing geometry out of some LEDs. You could build them like some specific level of detail. You could build them out of the real ones that you use in your scene right now. You could have some mix. There is like a bunch of stuff. There is a bunch of compromises. We just did alpha testing. The way you do alpha testing in ray tracing is like you trace a ray to the triangle, but to the first triangle. But if the triangle has an alpha texture on it, you have to sample the texture using the UVs that you need to extract from like someplace in memory. And then if that alpha value is less than 0.5, you have to continue tracing the ray through the rest of the scene. There is no way we'll get to any of this like complicated, intricate stuff today. Today, the aspirational goal is to lay the groundwork, and the groundwork is build the BLASs from whatever level of detail, build the TLASs from whatever level of detail, connect this to the shader, and like, you know, hopefully it sort of works. The other note I want to make is this. So ray queries are obviously running inside the shaders. Acceleration structure build can be done in the shaders. It, in theory, can also be done on the CPU. Because in theory, BVH data is just bytes and bits in memory. The format of these bits is unknown to you, unfortunately. There's no standard format for BVH. But you know it's just bits in memory, fundamentally. Nothing technically prevents the driver from doing this build on the CPU. In fact, the extension takes this into account and exposes an optional capability to build these structures on the host, as they call this. Unfortunately, on the driver that we are working with, which is RADV, this capability is not present at all. And so the BVH build is going to have to be on device, which I think for us mostly means in compute. The compute shader is not ours, thankfully. It's written like by the driver developers, but this code runs on the GPU, so, you know, as usual, all of the usual disclaimers on the stream apply, like, you know, if you make errors, something may go wrong, will crash, etc. We'll see. I think that's all of the introduction. And this is the extent to which I understand this space in abstract. There's probably details around the extensions that are going to be very surprising that we will find out in a moment. But that is the plan. As usual, we'll like cut corners, you know, if we find a way to cut corners. Unlike last stream, so yesterday I said is descriptor indexing really crucial. Our renderer just can't function without this, like we have to have it. With ray tracing, for now at least, I want to have the option to turn it off. It's going to be a little bit more painful because we'll have to like do some more specialization constants and shaders and ifs and BLAS. But one thing, for example, that I'm expecting is the cost of this is going to be not insignificant. We are rendering the scene right now in 0.86 milliseconds. Under a millisecond, there is no way we're under a millisecond if ray tracing actually works. So I want to have an ability to disable this from performance perspective. Also, not all drivers may have this. Not all GPUs may have this, etc. At some point, maybe we'll start relying on ray tracing as like a non-optional feature of this renderer, but for now, I want to keep it optional. It doesn't mean I want to replace ray tracing with other, like, I don't want to do shadow maps on this renderer. So if you don't have ray tracing, I guess you don't have shadows, but you know, it's still, you still have some geometry rendered. I think that is it. I think that's the entire introduction. And now we can actually start writing code. I think. I don't know that I forgot anybody. And I should have said this before. I know a lot about GPUs and raster and stuff like this. I know very little about ray tracing details, both the software and the hardware details. So maybe even in what I said right now, there is some glaring omissions or errors, and people who worked with ray tracing for a while probably are aware of these better than I am. So I think from this perspective, I'll try to, like, you know, educate myself on these topics quickly, but just be aware that I'm not an expert in ray tracing by any stretch of the imagination, neither software nor hardware. And so there's going to be exciting things to find out. All right, I think we're ready to start writing code. Let me look at chat. Descriptor indexing for SSBOs when attempting a bindless approach. So I don't know. We only needed this for textures. And I don't see a strong reason to do bindless in this render for other resources, because for other resources it's more practical to pack them in buffers. And there's efficiency gains. The thing I said about buffer device address in the beginning of the stream, where it's fine to use it. It's fine to use it if your alternative is many individual objects bound through bindless or non-bindless workflows or whatever. But there is small efficiency gains that you could extract if you don't do that in some cases. For example, when you do a descriptor read or a pointer read or whatever, it's like an indirection, and it may be faster in some cases to, well, like in theory, I think the world of GPUs is converging to the point where things like this don't matter a whole lot, and it's fine to just do bindless on like every single type of resources. So I don't think there's like a huge problem, unless there's some Vulkan thing that I'm not aware of that's specific to SSBOs. I don't think that's a huge problem to do this for SSBOs. It's just that I think it's like less critical to do this. But yeah, I don't know. I don't know if there is Vulkan specific reasons to avoid this for SSBOs. But the main reason why we need it is for textures, and I think textures is like the 80% use case of bindless. Having said this, I think eventually it might be nice to see a bindless only API, like a Vulkan 3.0 or distributed 12 is kind of going there, right? Because distributed 12 from some point, from some version that I stopped tracking, it has like powerful support for bindless and kind of expects you to do most stuff bindless. So is it possible to use SDF to trace arrays against? Yeah, but you have to build SDF yourself. The SDF will be very bad at representing very small details. For example, the leaves should cast very nice shadow on the building, not today, but at some point when we get to alpha testing ray traced data, you should have these leaves cast very nice, very detailed shadows on the building. This is very hard to do with SDFs just because SDFs usually don't have anywhere near enough resolution for pixel shadows. You could combine SDFs with screen space ray tracing without using hardware ray tracing. That is okay. Some games do this. You might want to do screen space ray tracing for context shadows in addition to ray tracing, but it's not always ideal. So we will not be doing SDFs. Yeah, it's not like it's not something I want to explore on the stream. Since bounded boxes either contain other boxes, triangles can be extracted with meshless. I will skip this. Can't really comment on this. The one thing I should comment on is I talked about triangles. There is one more thing you can do. When you build BLASes, instead of building this hierarchy where the leaves contain triangles, you can just contain the leaves empty. And inside the shader, you can say, oh, I want to hit array against this bounding box tree. And instead of getting a triangle hit at the very end, I want to get the smallest box that it hits in the end, right? Why is this useful? For example, maybe you want SDFs, but maybe the way you want SDFs to work is not, oh, I have one SDF across my entire world, but more like I have these tiny SDFs everywhere in my world, and then I built a bounding box tree around them. The GPU will not know how to trace array through the SDF, but it will know how to trace array through the bounding box hierarchy. It will give you the bounding box, and then in software, you can use bindless, you can use buffer descriptor object, you can just pack stuff in one buffer, and then you can extract the SDF as a buffer, maybe as a texture, whatever, and then you can trace array through that in software, right? So you can combine hardware ray tracing with software ray tracing, essentially ray casting, however you want to call this, through interesting structures. I know people try to do participating media like this. So if you have like translucent objects, like think about fog or smoke or something like this, you do some complex simulation, then you do ray tracing with it, but you want to integrate it into the scene, so you can combine this way. There's a lot of stuff you can do with this capability. Like, I'm interested in exploring what this capability can do. So yeah, in theory you could do more with boxes than with triangles, because inside a box you would have some software code that does something yourself. All right. Yeah, I heard DirectX 12 with 6.6 SM is like very, very convenient for bindless. So, okay. And yeah, no mist shaders, no hit shaders on this stream or on this series of streams. We will definitely not be using ray tracing pipelines. The theme, one reason is, again, like, it's just the software abstraction. I don't like it. It's too far from hardware, etc. But the other thing is, if you notice in the streams, we are not building a very traditional renderer where there's individual objects, individual shaders, BRDFs, etc. We are trying to consolidate things to as few kind of we're trying to pack as many concepts in like one unit as humanly possible, right? And do as much as we could with like as little as we can afford, or whatever. And so from this perspective, I'd rather have this very strong constraints. Oh, it's hard to do multiple BRDFs because when you do like ray tracing, you have all of these different shaders. Yeah, that's cool, but it's a good restriction to have, sort of, from the software simplicity perspective, even if maybe you can't achieve the peak quality. So I think when you think about the ray tracing, when your job is to like build a path tracer with a lot of different types of objects and materials, I think you gravitate towards ray tracing pipelines. But our job is not that. Our job is to build a very simple renderer that can still sort of punch above its weight, if that makes sense. All right. But honestly, I just don't like ray tracing pipelines. This is all just post-factum rationalization for not using them. All right, so ray tracing. So our first job is to build acceleration structures. Well, our actual first job is to like, initialize the extension and all of this stuff. So let me switch back to debug because we need validation support. And then we will be trying to use the fast mode, I guess, to help a little bit with iteration time. So we talked about this last time. And again, I'm personally in... Wait, that is new. Interesting. Hey? Oh, yeah, that's because I didn't actually, oops. Oh, yeah, the timestamp is just, sorry, hold on 1 second. I messed up the previous change, because of course I did, because I forgot to do 610. Wait, well, hold on. 2, 6, 8, 10. Do we have 4? 1 moment. I need to fix this, obviously, because we should have validation working. At some point, a lot of this code should probably be refactored, but I've tried to do things very incrementally so that you can follow the progress to the extent that it's like practical to develop a large project on like few streams. So some stuff is like not ideal. So this guy uses 2. I'm confused as to why these indices are so weird. Yeah, and this says we only have 4, which is not right. So this should be using 2 and 3. What is using 4 and 5? Oh, are there 2 slots? One moment. It's been a while. Oh, the pyramid is using 4 and 5. The pyramid is tricky. Okay, so this is, what is it using? Oh, 0 and 1 are the frame count. Okay, so this is 2 and 3, and then this is 4 and 5, and then this is 6 and 7, and then this is 8 and 9, and this is 10 and 11. These indices are out of whack. Okay, so then this is going to be 12, and then this is going to be 14, and we do not count these, which is not great. Oh, and then there's the pipeline. Oh boy. I should have done this. Okay, I should have done this before. It's fine. Some counters are a little bit messed up. Let me just do this for now, and then I'll fix some triangle counters like later. No, it still wants to do this. Okay. Because yeah, when we render, I forgot about this. Dun, dun, dun. This guy, how's it always using 0 though? Oh yeah, okay, this is the, okay, never mind, this is all good. So this needs 6, and then this render is 2. Wait, this doesn't need, this just needs 4. 4 is fine. Interesting. Not sure why it said 4, because I think it should be 2. All right. And then I think I forgot to destroy some shaders, as it were. This is the consequences of very quickly doing the alpha test thing that I was talking about. So we now have mesh link pipeline, mesh post pipeline, and then we now have a cluster post pipeline, and then the other stuff I'll just delete in the future. All right, and then let me fix the counters while I'm at it. So now there's 3 things, and then you need to aggregate them. Eventually we'll replace the profiling with like nicer code, but for now it's fine. And then I guess the vsync, oh no, the vsync is off. Oh, this is because, oh my god, yes, oh good, sorry. The downside of using the fast mode that I talked about last time is it generates less efficient structures, and so you get less efficient rendering, so you get different frame times. Let me just double check that with fast 0, things are fine. But okay, sorry, this was, again, I did this very, very quickly today before stream, so obviously I did not check in debug. No, this is still... right. Right, let me actually check in release then. This is confusing. Because the stuff I've done shouldn't have... Yeah, okay. In the release it's fine. Interesting. Usually... Oh, the validation overhead. Yeah, so the difficulty of profiling code... let's just do this. The difficulty of profiling code in debug is that not only does the CPU code get slower, but also the GPU code may get slower as a byproduct, even though I have vsync disabled. The CPU takes like more time to do validation and stuff, which slows down the what do you call it? The GPU uses dynamic clocks, and like I don't have a great way to fix these clocks so that it has stable performance results. And so there are some deltas in the timing, in the GPU timing that we are collecting that don't always make it easy to like assess the performance. Anyway, whatever. So I think we are fully done with the actual introductions and the pre-ray tracing work that I was talking about. So the first thing we need to do is to initialize the extensions, to request them essentially, and then to build the acceleration structures. And then, as I was saying, I am gonna keep like a boolean, and ideally I also wanna like switch it in runtime. We had like this mesh shading supported also somewhere, yeah, because for performance it's very nice to be able to toggle like ray traced workloads in general, maybe not just shadows, like on and off, but very likely we will not be able to do like, if at the end of the stream today we get checking for this is painful. So there's two extensions we need. We need acceleration structure. And then we need queries. And technically you can have one without the other. This is why there is this pipeline query split, because it's kind of DXR 1.0, 1.0. And so it's not quite right name, but it's fine. But we need both. There is nothing useful we can do if we just have acceleration. Maybe just testing queries is enough, because it would be weird to have queries and not have... You know what, let's just test... oh, yeah, okay, yeah. Let's just test. I don't know how it's possible to have queries but not have acceleration structure support, because queries rely on acceleration structures to be able to do the query. So that would seem like a broken driver, so let's just do that. And then this, and then when we create the device, we say, hey, do you want ray tracing or no? And then if you do want ray tracing, then you want both of these extensions. And then you also, in the typical Vulkan fashion of being needlessly annoying at times, ray query, yeah. You need to like enable this, and I think it's 1.3 maybe. So let's look at, so as I already said, this is not true. We're using GitHub Copilot, and it is not always, no, this is not, oh, no, yeah, sorry, this is not core, this needs to be chained. Now we have two optional chain structures, which makes the linked list painful to construct. Ray tracing supported. This is even worse. Okay, let's look at the booleans. So we need to enable ray queries. And the other thing we need to, so we need two, all right, sure. Ray query features. And then you have the second struct, which is the acceleration structure. Physical device accelerate, surely. Yeah, okay, this guy. So what do we have here? We want acceleration structures as the main thing. There's a couple more things that you can request. I already talked about this thing. Our driver doesn't have this, but if it would be nice to be able to build the geometry on the CPU just to make it simpler to like debug and like stuff like this. There is some stuff related to the bind list that we've talked about last time, which we don't really care about right now, so it's probably fine. It's nice to, we'll try to just have like a single acceleration structure for a top level. So I assume we don't need like bind list setup for ray tracing, but if we do, it's useful. Capture replay is support for debugging tools. We'll ignore this for now because I think RenderDoc doesn't do ray tracing anyhow. I didn't double check, but I assume indirect build refers to the ability to do the build of the TLAS from the results produced by the compute shader, where you don't know the count of the things that you're trying to build ahead of time. For now, we don't care, because for now we are not going to solve the LED problems, etc. Both for ray tracing, both for reflection tracing and for shadows, you want TLAS for invisible objects to some extent, because objects that the camera doesn't see can be reflected or cast a shadow. So even if we did some indirect build, we'd need some custom setup for culling, and I assume you can do a TLAS build without doing the indirect build, because you know the count, because it's like all objects, it's just the LEDs are different. So anyway, we are not gonna touch any of this stream anyhow. So for now, we just need the structure, and that is it. And then we need to chain both of these extension structs to, like, you know, the main linked list that we have. Let's chain, let's chain, it doesn't really matter. Let's chain this to, and let's do ray tracing, because the name is really weird otherwise. I believe the way the KHR extension is like based on an NVIDIA extension. I think there was just one NVIDIA extension, but then they split it into 3 like this. But, you know, again, because we only need 2 out of 3, I can't really complain, because I don't like the third one. I only like 2 out of 3 anyway. So, and then we need to chain this guy. And then the chaining of this guy is like weird, because we can have mesh shading or we cannot have mesh shading. So all right, and then this guy goes here. Okay, so I think this is roughly enabling ray tracing extension. Let's find out. Oh, I don't want this. Why does it require it? I mean, I know, okay, this is a little ridiculous, but okay. So the closed builds that our driver doesn't support anyway refer to the ability to tell the driver, hey, can you build the BLAS or whatever on the CPU for me? But this might be a slow process, so they introduced another extension which allows some thread management, but like we don't even use this. We can't even use this because the driver doesn't support this, but I guess they have an unconditional dependency between the exploration structure extension and this deferred thing, even for drivers that don't do host builds. So that is fascinating. Okay, so the hard part is done. So now we have the ray tracing extensions activated. Maybe we forgot something. I should say I'm hoping when we did NVIDIA mesh shaders, we did it super early. So we hit all sorts of validation issues, drivers, things like it was rough. I'm hoping that the validation layers are in a really, really great spot from the ray tracing perspective. So if we have issues in the code that we are writing, the layers will tell us about them. Hope springs eternal. So BLAS and TLAS. So BLAS is built from geometry. So this is our first task. How do you build BLAS from geometry? So BLAS, as I mentioned, is sort of just memory, just bits and bytes, but you don't know how they are organized. And as a proxy of this, so we have like a lot of triangles. How do you build a tree out of a lot of triangles if you know nothing about this tree structure? Well, the driver knows how to do this, but you don't know how much memory it will take. And because it's Vulkan, memory management is explicit, so the driver has a function that allows you to ask, given the stuff that I'm trying to build, how much memory does that require? So that's our first challenge. Feed all of the geometry into this function and get a number back, or numbers. I don't even know, multiple numbers? No, yeah, just... Oh, and then there's a scratch buffer. Yeah, okay. Now, we could do this one mesh at a time. And I was hoping that the driver supported host builds, because with host builds, generally you care a little bit less about small concerns like this. But because it's all in compute, I kind of just want to take the entire set of meshes that we have loaded and just ask for BLAS for all of them at once. So that's what we are going to attempt to do. So we're going to call this structure with this function, pass it all of the meshes in our scene. And remember, we have the separation, we have the meshes, which are like the geometry, and then we have the draw calls that are instances. So we only care about the meshes right now. So we're going to call this function with all of the data and ask it, how much memory is this? And we can do this after we've loaded the scene. We can do this after textures. That's fine, I guess. This is draw calls. This is meshlets. I guess we can do this. Oh, yeah. When you give the driver the geometry, so somebody asked about meshlets. We are sort of fortunate in the fact that we haven't removed the traditional pipeline yet, because when you build ray tracing BLAS for geometry, you give it triangles. What is a triangle? Well, it's vertex and index buffers. Well, we have vertex and index buffers. The only reason why we still have an index buffer is because we support dynamically disabling the mesh shading pipeline, which is going to play in our favor because this means we can just pass this buffer hopefully to the driver, and then like it's going to be good. So let's just go at the very end here and let's start writing code here and then hope that this works. And I want to write it like in a separate function from the get-go, and then I'll just pass like stuff to that. So we have this geometry struct, and then we have vertex buffer and index buffer buffers, and then we have scratch, which is going to be useful, and then we have the command pool and command buffer and q, and we will want to generate this somewhere. And this is not BLAS, this is BLAS S, sort of like, you know, it's like multiple structures. But these we're gonna find better names for some of this stuff in the future. Okay, so I wanna go here. In geometry, and then we have this vertex buffer thingy, index buffer thingy, scratch. And the reason why we need command pool and command buffer and command queue is because, as I said, because our driver doesn't support host builds, we have to do this on device. Well, guess what? This means submitting commands to the device and then like waiting on them and stuff like this. So, and then geometry struct has the vertices and indices, which we don't, this is going to be gone from us at some point. But the main thing it has is the meshes. I actually don't know if I'm going to get one object back. I don't really know how BLAS, we'll find out. As I said, I have very little context from now on. So, but I guess we can do, let's do geometry for now, it's fine. So we want to call this function, and then the build type is basically saying, do we want to build on host or on device? We're going to build on device. Device builds are not optional, host builds are optional and unsupported. And then you tell it information. So you tell it how many geometries you have, which is the number of meshes in our case. And then for every geometry, you presumably tell where to get the data from. Scratch data. Oh, right. So I think a lot of these structures are, you have these two-step operation. This is kind of common in C APIs. You get the size, then you allocate yourself, and then you pass the allocated buffer to the APIs to build. It looks like the structures for a lot of these are shared, which is nice. So it might be that we can fill the structures once for the most part, and then just pass them to the driver twice, and then it's going to work out. Okay. And then I'm planning to cheat and to reuse the scratch buffer that we already have. And if it doesn't fit, then, you know, ray tracing doesn't work. It's fine, because cutting corners. Okay, so anyway, it's interesting that it returns void. I guess it can't fail, but it's kind of interesting because, anyway. So we are building on device, and then we have build info, max prim counts, which I'm not sure what this is, and then size info. This is going to be the result of the function. So our first challenge is to call this function, quite literally. Does this have like an S type? Of course it does. Build sizes info. Okay, let's see. So it will tell us the structure size and then update or build, right? And then the scratch sizes. Update is this refitting thing that I was talking about. Build is like the actual build. We only care about build for now. So we will need to essentially call this function and then allocate this buffer. And this is going to be where the data lives forever. And then the scratch is, I guess, going to be used as a temporary memory by the driver. Okay, so, and then I'm not sure what the max primitive counts is. Yeah, so this is just, it's interesting that it's separate, but okay. I'm not gonna, last time I questioned a lot of parts in the API because when you know the full stack, you can look at the individual decisions and ask why. But since I know nothing about this yet, there's going to be things that feel weird to me, but they're likely done like this for a very good reason. But okay, so this guy is going to be separate, but it's basically just the number of triangles in each mesh. Oh, and I should say, if people who are watching this are familiar with ray tracing and spot things that I am doing wrong, please write so in chat, because it is going to be likely that we will hit some weird issues that there's not going to be, that I will not have, again, good intuition for. And oops, right. You know, having help with that will be helpful, but it's probably too early for us to run into any significant issues, but in general. So, and then we basically just need this build info thing. Consideration structure, build, geometry, info, yeah, that tracks. And then after we call this, we are hoping to get this, and then we get build scratch size. Okay, so now the actual thing that we need to fill is this guy. So this has the type, which is this bottom level BLAS. Okay, and then wait, let's go back. So then flags. One thing I'm super unclear on is there is all sorts of intricate stuff that it's eventually we are gonna explore around like extra data that you need, like so to just trace array through the structure and get a binary result back, yes or no. You don't need a whole lot from, you just need to feed the driver the geometry basically, right? But when you want to get back a triangle and ask, oh, does this triangle have a texture with alpha testing on it? Oh, it does. Can you give me the ID of the texture and the texture coordinates? Things start to become interesting, right? So mostly going to ignore this for now, but there's going to be stuff in this code that we'll have to change in the future streams to actually make it work for what we need to do. But oh yeah, and there's also this thing called compaction, which I would assume we don't need if we just build it from scratch, but maybe I'm wrong. We'll see. I don't fully know this enough to like explain it, but we'll skip it for now. And then, yeah, when you build it, you can say, oh, I want to maximize the efficiency of the ray tracing, or I want to maximize the efficiency of the build time. Or I guess you could specify both, and then I'm not sure what it means. But we want, and you could say nothing, in which case I guess the driver will figure it out. For now, we'll say that we want maximum trace performance. And then you could also say, oh, I want to conserve memory, which I guess we can check this flag later to see whether it saves us memory and how much. That's going to be interesting. Oh, the other thing is, obviously, all of the behavior of all of this is driver and hardware dependent. We have an AMD GPU and an NVIDIA GPU. Things could be different. Very different. So it could be cool to test this code on NVIDIA in the future, but for now it's all AMD. And I've talked about the refitting and updates and stuff like this. You could say that you will want to do that. We don't care. The compaction, I'm kind of curious about, because I'm not sure if the initial data structure that we are going to get out of the driver is already compacted or not. I would expect it is, but maybe I'm wrong. And then there's some newer NVIDIA stuff that we can't really use, so that's fine. Okay, so that is our flags. So then our mode is we are building. And then I'm assuming these are null because we don't have anything. Oh, I guess, right. The way probably it works is when you build, you get the sizes, and then you allocate the structure, and then you set this guy to the object, and then you call the function again with like the pointer. And then this guy is probably for updates when you have the original one and then you want to apply modifications to it. So ignoring this for now, I mean, this is going to be like important later. And then we have build info, geometry count is the meshes. And then there's like these 2 pointers, and I'm not sure why there's 2. Let's see. Is a pointer to an array, and then a pointer to an array of pointers. Not sure why, right? Only one. I guess like it's a little weird, but it's fine. Okay. So, and then scratch date is null because we don't have it yet. And again, these are the 2 things that we will need to fill after getting the sizes. All right. So this is the main event. It's a little confusing because I have this struct called geometry, which is like all geometry in the world. And then here geometry means like a single mesh. So the names are a little bit off between my code and this code right now. But we can adjust stuff later. All right. And then we need to fill this guy. What does this have? Oh, it might be better to fill this guy here because this is going to depend on LODs. All right, so what do we have here? Oh, we have S-type, of course. Oh my god, these names are annoying. No, geometry, isn't it just geometry KHR? No? Interesting. Yeah, this guy. So you can see the autocomplete in my editor was never prepared for these giant names that like don't fit on the screen and like don't fit anywhere. So the type, this is the thing I was talking about with boxes where you can do hardware software ray tracing combinations by just tracing ABBs, but we only need triangles right now, and then after this we'll need instances to build TLAS. Instances are objects. But this guy is building BLASes, so it's geometry type. And then there is the geometry, which we will look at in a moment. And then there is flags. Let's see. I don't know what this does, but our geometry is opaque right now. I am curious though. No, that is not what I wanted to search for. Okay, this is some non-ray query nonsense. Which is, I guess it's probably fine to set it, like it doesn't matter. Okay, and then the actual thing I assume is here. Okay, and this is a union. And we need triangles, which is this guy. Let me actually fill this one here, and then geometry triangles. Okay, so S type, nonsense. Okay, so this is the actual data that you need to pass to the driver to tell us this is my vertex data, this is my index data, and this is my transform data if you're building. Oh, yeah, right. The way this works is essentially you give the driver the objects, the geometry, but you could ask the driver to transform each object with a transform matrix. We don't need this, I don't believe. Yeah, we don't need this. This is like useful if you want to build BLAS from a static scene, like a single BLAS from the whole static scene. I would like to keep the separation between instances and geometry and keep the individual meshes in their own BLASes. This is not necessarily the most efficient way. So what we could also do is build a BLAS from our entire scene with the transforms for every geometry, like a single one. In fact, will this actually do this? This actually might do this, right? Oh, I think I might have to actually call this guy twice to do what I want. Oh, I didn't realize this. Yeah, this is probably building one BLAS, and multiple geometries is just like a way to pass multiple data objects, because this guy just specifies one thing. Oh, interesting. Interesting. I mean, we could forgo a TLAS for now initially, I guess. But this is a little awkward. Okay, I did not think this through, obviously. So then actually we only have one geometry if we want to maintain the dynamicity part. How should we do this then? Will I be able to just trace BLAS? Or will I need like a dummy class? One moment. So we are gonna call get size, and then we are gonna call create, and then we are gonna call build. And create is gonna give us an acceleration structure handle that could either be a BLAS or a TLAS. I see, interesting. So it's gonna be bound to a buffer, then it's gonna be populated with the CMD build. Yeah. Yeah. So I guess we have an opportunity to build a single BLAS first for all our meshes. How should we do this then? Because the heck. Alright, one moment. I didn't look into how you build classes too much. So I want to look into this a little closer. Normally you'd build like a BLAS per object and stuff. The issue with this scene, or not an issue, but in this scene there's way fewer meshes than there's mesh instances, which is nice. But this kind of means I want to build a BLAS per mesh if I want to optimize for memory consumption. And I kind of wanted to do this anyhow. I'm just not sure if this means... I guess it just means I'll have multiple objects, many objects. Okay, hold on. No, this is wrong. Hold on. No, I don't want this. I want something else. So CMD build, and then oh no, this is interact. This guy. No, you can do multiple acceleration structures. Oh, this is what this ranges thing is for, right? Didn't get size have this as well? Or is get size... Okay, I think I'm doing the right thing. I was just confused AF. So when you call CMD build, you can do multiple, because it says pointer to an array of info count pointers to arrays of build range info, and each one is a pointer. So many pointers. Dynamic offsets as defined by binfos. So yeah, so you can do this in one call, at least in one build call. But this means you'd have to pass multiple. Oh, maybe you call get size. Hold on. Oh, this guy has info count and that guy didn't. Oh, so you query the size one at a time, I think. And then when you build, this is what I want, right? Okay, yeah, this is what I wanted. I don't want transform data stuff. Okay, hold on. So when I build, I will want to say this is my mesh count, and for every mesh I will have this guy. And that's going to be maximally efficient because it's going to build all of them like at once in parallel on the GPU and stuff. Okay, so then I need more than one of these guys, and then I need to query the size for every one. So this is not quite correct. This is not quite correct. All of these arrays are not... and this is all host data. Okay, so actually what I want is I want a vector of these guys as well. Build infos. And then for every one, I am going to add a build info. Okay, I think this is right. And then build info is gonna have this as type, and then type, and then actually every build info is only one mesh, and then it's gonna go here. Okay. And then I will just query the sizes individually. Okay. And then the primitive count, there's just one. So it's primitive counts I. And then size info. Okay, so I think this is more correct. All right. So now let's go back to this. we are supposed to specify vertices and indices, and this is all data on the GPU and transform data. So transform data is null, we don't need to specify it. And then I'm assuming we can just pass the data to our vertex buffer and index buffer, which I have these here. So this is, and I assume when you get the sizes, you may not even want this data. Like, I would guess there's some worst case bound for that's just based on counts, basically. So I would guess that this specific stuff, max vertex, is probably used. So some of the stuff is definitely going to be used by the driver. I'm just not sure if the whole thing is going to be used. But because we are going to do all of this in one go, we might as well fill the entire struct like however we want this to work, basically. And okay, yeah, so our vertex positions are stored in the floating point format. We could assert something. How are we gonna do that? Let's static assert here that offset of vertex, I forget if it's like BZ or something like this, is equal to size of float times 2. It's like, well, is equal to offset of vertex Vx plus size of float times 2. This is not the strongest assertion in the world, but just this format, if we ever switch positions to half precision, which I will do at some point, we're gonna have to switch this code. Oh, and also somewhere in the spec there is a table and way to get to ask the driver, do you support this format of vertex positions or not. I'm just gonna ignore this because, you know, let's just assume, I mean, floats must be supported for sure. There might be other. Oh. Does it want buffer device address based stuff? Because I can't. Oh, I didn't even realize this. We might have to start doing device buffer address. I thought you could pass like a buffer with, but yeah, this says device or host address, so clearly interesting. Okay, so ignore this for a second, and then vertex stride is size of vertex. Max vertex, I'm assuming, is like the maximum value of the index of the vertex, which is just vertex count, which should be no, not -1. Oh yeah, it's not lot specific, it's just this guy. Wait. Okay. And then our indices are 32-bit, I believe. And then our index data again is, I actually need to read this. All right. So my first question is, do we need vertex data to actually know, to actually build, or to like get the sizes, or is it only necessary for building? Okay, geometry data, triangles. So I'm gonna guess that this relies on buffer device address for device builds. I'm just not sure if we need this to compute the sizes of the structs. I guess we could run this and see what happens. We are not using buffer device address yet, but there's no. Yeah, okay, the sizes don't need this data. Okay. So we have a bunch of code that is now going to produce the counts of bytes for both the scratch and the acceleration structure itself. So that is cool. This is the data for like every single mesh in our scene. So now we need to add these up, allocate it, and then actually pass build, and then actually run the build. And then when we actually run the build, like we'll actually need, you know, the full. I wonder what the alignment requirements are, because yeah, I see. So this properties struct has restrictions on the alignment. All right, we'll need this. We will need this. Because what I want is I want to pack all of this data in like one buffer. But to do that, I need to know. This doesn't have an alignment, right? It says added a property to the struct. Oh, this is NV struct. No. Whoa. Oh, there's no KHR struct. Oh, okay. It's probably like ray acceleration structure. Like acceleration structure properties, this guy. Yeah, okay. So it has no alignment restrictions here. It's interesting that I don't see. This is a little bit confusing. Oh, cool. This guy is just not here. Okay. I'm surprised that there is no parallel version of this guy. And then it's at least 256, but maybe smaller. I'm surprised that there's no version of this for the actual structures. That is surprising. But okay. So then when we call the build, in addition to vertex data, so we are going to allocate a bunch of acceleration structures inside one large buffer. And then when we actually build, we are going to pass it the address of the scratch data, and then the structure itself, and then the structure will contain the offset. Okay. Oh, I guess like when you query, I see. So when you create, you will tell it the buffer inside of which to create it. Oh, okay. So the alignment is restricted to 256 bytes as a hard-coded value for structures, but for Scratch it's customizable, but it's at least 256. Okay. All right. So required by spec for offsets could be for acceleration structures, could be smaller for Scratch, but it's a small waste. When you when you pack multiple things together into one buffer, usually individual things should be aligned, and I was trying to figure out how much should they be aligned by to correctly compute the total amount of Scratch space and acceleration structure space that we will need. It looks like the value is 256, that is mandated by the spec, and the only custom version of this is for Scratch, which we don't care about. Okay, so then now we are ready to say total Scratch size and total acceleration size. The word acceleration structure is so freaking long. That is unfortunate. So we add we add size in for acceleration structure size, and then we round it up to alignment, and then we do the same thing to Scratch. And then with Scratch size, and then we should record. Oops, wait, I pressed something weird again. And then we should actually record the offset. Acceleration offsets. And then we should record Scratch offsets, because we will need them in the future. And then we might as well also have PK acceleration structure geometry. This guy. Okay, so let's just keep these aligned. Okay. So I think this is correct, hopefully. And then all right, so now we should get the complete memory requirements for all of the acceleration structure stuff. And let's see how much memory we need. Whoa, that is a lot of memory, people. 400 megabytes of acceleration structures and 162 megabytes of Scratch buffers. Whoa, that is a lot. That is like way more than we use right now for the geometry part. This is also why I didn't want to just do the single BLAS for the whole scene, because it de-instances meshes. So if you have two copies of the same bush, you could build a total BLAS from the geometry that has both of them in it, but that's inefficient. But wow, this is a lot of memory. We have this much memory. We have like 2 gigabytes of textures, so like I guess it's fine, but whoa. And this is not a geometry dense scene. Okay, people, interesting. Let me check what happens if we like ask for less. I think this is, no, this was the flag. So if we ask for like, if we ask for less memory, what do we get? Whoa. We get the exact same thing. So I'm guessing the AMD driver disregards this guy. So let me check what the compaction flag does. Oh my God, I have too many tabs now. Oh, it's like a copy with compaction. We are gonna ignore this for now. I'm not sure that it's critical. It'll complicate stuff for us a little bit, so I'm gonna ignore this for now. Okay. So that is a not insignificant amount of memory. Oh, and by the way, I want to build all of these structures in parallel, but actually, as you can see, so the acceleration structure size is what it is. This is what's required to hold the memory, the data in memory. These crash structures, if you only build one at a time, you could fit these into like a smaller amount of memory. It will complicate our code to build one at a time, and it will also make it slower to build one at a time. You could have some dynamic thing where you have a scratch buffer of a fixed size, which we actually have one, and then kind of say, oh, build however many fits in this, and then, you know, cycle the structures this way, basically. But I guess for now, it's half the size of the structures, which is still a ton of memory. But for now, I guess it's going to be more complicated to do the right thing. We will not have time to draw an array today, I fear. I didn't realize that you need to pass in the buffer addresses. Okay, that's fine. So I have a scratch buffer that I use for a bunch of stuff. It's not quite large enough. And of course, you want to be dynamic to adjust. Okay, that is fine. So then let's have this guy create the BLAS buffer and the scratch, and then let's actually move this guy BLAS buffer, scratch, and then all of this rest is the same. Okay. This will not be a short stream. I can just feel it. The issue is we'll need to build TLAS, and that will have to have a bunch of like a bunch of stuff. Yeah, all right, fine. So, but at least there is only going to be one class, so it's kind of the same code. It's all a little annoying, but it's fine. Okay, so, and actually we could even reuse class, we could reuse the scratch buffers for, if we only knew how much. Okay, we will work with what we have. Let's just go through this one thing at a time. So we computed a bunch of stuff, we computed the sizes, so now we can create the buffer, both buffers, which fortunately we already have a helper for. So we need a BLAS buffer. Oh, and for this we need this memory properties. No, I don't know. The order of parameters here is completely crazy at this point, but memory properties, something like this, right? Yeah. Which we'll fix later if it comes down to it. Go back. Okay, so create both buffers. I'm not sure if you need to round the thing like up more to create it, but probably not. Okay, and then I guess there is like buffer usage ray something. Not NV, it's something else. Alright, hold on. Autocomplete betrayed me. Alright. Yeah. So we... Oh, this is probably going to be important for the vertex data and index data. But these guys will need this. And then the key memory properties device local, presumably. And then I'm not sure what this storage, the scratch buffer is a little weird, because like you technically aren't storing data there, but I'm not sure if it needs any specific usages, but it might need the same one. Let's keep it like this for now. And then I'm guessing that this thing will be necessary for index buffers and vertex buffers, but probably validation layers will tell us. So, total scratch size and BLAS scratch. Did I just call it scratch? I just called it scratch. So, oh, we could reuse the scratch buffer. Actually, this is fine. Okay, this is fine. And we can even deallocate the scratch buffer after we're done with this. So actually, because it's all going to be synchronous for now. Oh no, usage can't be 0. Yeah, I'm not sure what the usage is going to be though. Let me look at this guy. Because build input read-only feels weird for the scratch buffer because it's not read-only. So like that is odd. I'm a little confused by this because I expected there would be a usage bit, but there isn't. And Vulkan really wants me to specify something. Let me specify this for now. This must be wrong. And then actually, because it's all going to be synchronous anyway, let's simplify this guy and this guy and this guy. And we'll just have a buffer called scratch, and we are gonna just destroy this buffer at the end. Scratch device. Okay. So now that we've allocated some memory, although I'm really fuzzy on this guy, and we'll need to change some other bits like later, but I'm sure validation layers will tell us. I'm not actually sure if the code works, but let's check. So we just allocate the memory, we like deallocate it back, it's not very meaningful. Okay, so now we can actually create the acceleration structures. I wonder how many comments at this point right now in chat there are that are telling me that I'm doing things wrong for some reason, and I'm sure I am, but I want to create the structures and then I'll look at chat. So this guy takes device and then create info. This will have wiki check. So this is going to be it's probably not reasonable to break it like this, but whatever. All right, and then, oh, and this is the device address, so we can't actually build yet because we need to hook up the buffer device address stuff. Okay, that's fine. I will do this momentarily. Ignoring this for now because this is debugging stuff. Oh, no. Wait, this has buffer and device address separately. I guess it works with either. Oh, this is for replay. Okay. Ignore that. And then, okay, so that's fine. We can create them just fine. So buffer and then offset is the offsets that we've captured, and then the size. Oh, we didn't capture the sizes. That's a problem. So the size is the sizes, and then type is BLAS or whatever. Yeah, like bottom level. Actually, I wonder if you can build a TLAS from. No, that would probably not make sense. Okay, so this will work, should work, presumably. But then to actually run the build, we need to actually pass the data. And to actually pass the data, we need addresses. I am surprised that it simplifies stuff, so I'm not super surprised, but I'm a little bit surprised that when you build, so we allocated the structures. Let's now look at the build. Let me close a bunch of this stuff. So we are done with this. We actually need this. Let me close actually everything because it's faster to open it again. And then close this for now. Okay, so now we need to call this guy and we need to tell us that we need to build all of the stuff that we've just like been preparing, sort of. Oh, this is useful. Oh, this is useful. Okay. But then why can't I just specify the object? So we actually need, this is the thing that I was looking for that I missed, that I was missing in the other structure. It makes sense that it's here because it's only useful for build, but it's annoying that they really want me to essentially use, like I can't pass a buffer handle to the vertex data, I'm guessing. Because that would probably not work. Because it says address. I would have loved to just pass. Okay, that's fine, whatever. So let me confirm this in the spec. Because here it says the buffer. Oh, this is, oh, huh. This is what I wanted. So the NVIDIA extension had this. Okay, cool. All right, but the KHR extension, this is NVIDIA. The buffers from which the buffer device addresses are queried must have been created with the build input read only. So that's That's fine, that makes sense. Oh, here we go. Scratch data should have the usage storage buffer bit. I was sure it's not these guys. I just wasn't sure which one. Okay. So, I guess we need to get buffer device address. Oh, this is core. We probably need to enable this, but this is core. Okay, fine. I approve of this. It makes sense. Buffer device address equals true. Sort of only. We only need this if ray tracing is supported for now. It might make sense to do this unconditionally in the future. We've tried using it in the past, as I was mentioning in the beginning of the stream, and then decided we probably don't need it, but I guess we do need it. Okay, so, okay. So now we need to go get device. To be able to do this, you have to allocate the buffers with like a special flag. And then of course this function is annoying because it has like an info. Vulkan never change. Okay. All right. So we need this for the index buffer and for the vertex buffer, and then we will also need this for the scratch buffer, but not for the acceleration structures, if I'm not mistaken. Maybe for the acceleration structures later. Let's. I guess now that we have this, let's add a helper here. I understand why they did this, because this capability is... Wait. Oh, we had a function for this, amazing. So as I mentioned, we experimented with this before. We just didn't... Amazing. Okay, so I guess I left the function like for future, and look at that, the future is now. So that is hilarious. Okay, cool. We'll need to change the flags on creation of the buffers, but the validation layers will tell us about this. It is interesting that, so when I say vertex data, this is a little bizarre, because on one hand I have this address that I can just manipulate with however I want. So what I can do, what is the right thing to do, is to say VB address plus, yeah, so like just work on this address as if it were a pointer. Although this guy complains. Oh, because vertex, is this like an union device address? Okay, that's actually nice. And then index data. Yeah, that is, I think that is correct. The interesting part is, oh, and then, sorry, and then mesh doesn't have, yeah. The interesting part is that in addition to forcing me to use addresses, I guess they give me an option to use this double pointer array that has its own offset in bytes. Which is like odd, honestly. It feels to me like they kept this as is from an NVIDIA extension, but then they replaced buffer data with device address, and so now it's like not sensible. The combination is not sensible. I don't really care because I can just use zeros as offsets here. It's just a surprising combination, honestly. I don't, this part is like odd. Okay, so for this code to work, right now this will fail validation because the buffers in question oh, and I need this for Scratch. The buffers in question don't have the flag set on creation. I'll need this for Scratch. So for Scratch, hold on. So here, when we create the sum buffers, we'll need some additional flags. So ray tracing buffer flags. Only if ray tracing is supported. We will need this guy because this is the thing that you'll need for the actual build process. And then we'll need VK buffer usage shader device address bitwise shader. Surely this is just, oh no, buffer usage shader device address bit buffer usage. So why? No, okay, all good. And so we'll need this for the vertex buffer and for the index buffer in addition to all of the other stuff. No, not like this. That we specify, we will need this. So that is done. And then when we create scratch data, scratch buffer, we have too many scratch. So here we'll need the same shader device address because we will need to pass the scratch data pointer, and I think it's also not a buffer but like a pointer. Okay, all right, we are almost ready to call build. And then we'll have VK device wait for idle here. All right. Yeah, so I think we are basically ready to call build. I think this guy had the scratch data pointer that we'll have to fill, and it has the DST acceleration structure that we'll have to fill. After we create these, I guess we might as well fill them in here. So build info DST acceleration structure is the BLAS we created, and also the scratch data is scratch data address, no, device address, scratch address, scratch offset, so that's all correct. Okay, and now we can call this function. We're almost at the point, unfortunately we can't even start tracing the rays, because to trace the rays we need a TLAS, not just BLASes. And we're already 2 hours in. This is going exactly as yesterday went. It is hilarious. Okay. Okay, so we discussed this stuff before around, like, we discussed this stuff literally yesterday around temporary command buffers and such. And you will need some barriers probably for some of the stuff in the future, whatever, it's fine. So that is the synchronous build. And then in the synchronous build, in the command buffer, we'll want, and then I think we'll actually be able to build it last, like in the same function, because it allows us to reuse a bunch of stuff, which might be good. Maybe. We'll see. All right. So we want to call this function command buffer, and then we are building all of these guys at once. So that. And then we already have the build infos built. And then the only extra thing that we need is this like array of pointers. which it makes sense that it's pointers, sort of, because you could have, if we wanted to build one BLAS out of all of the meshes, we could write almost the same code, except that we'd only have one acceleration structure and then one build info, but we'll still have an array of geometries. This is the code I started from. So it makes sense that they have an array of pointers. It's just, I wish I could just put a null here, because this guy is useless right now. This guy is going to repeat the exact same information that I've already given the driver. This is the actual problem here. Like, this guy should be allowed to be null. Can it be null? The answer must be no. Because it has all of these restrictions that say, oh yeah, this should only... Yeah. This I will say right now, even though I have little context around a lot of this stuff, this to me looks like an API usability problem that did not have to be here. Because this is just busy work. Like, what I'm doing right now is busy work. What I've been doing before, at least, is like you give the driver the information, but this is busy work. This should not have been here. Well, or the pointer should have been optional. There's cases where it's valuable to have, but this pointer should have been optional. Build range PTRs. Okay. Let's fill these guys here. In fact, I guess let's fill these guys here. So we need to fill this struct, which is fantastically useless. This guy is 0, this guy is 0, this guy is 0. The only thing we need here is primitive count. If we ever switch from the first lot to something else, this code will explode. That's gonna be fun. I mean, ostensibly, we've just built some acceleration structures. There is no way to observe that behavior because, you know, the code doesn't have any errors, but ostensibly we have just built some acceleration structures. So I low-key hate this part. Oh yeah, okay, this thing I can just extract from build infos geometries. There's only one, and then geometry triangles, and then oh, am I wrong? Maybe I'm wrong. No, this can't be right. Hold on. Where is the... Oh, this is primitive counts? This is primitive counts. Yeah, this is primitive counts. This is incredibly redundant. It's only a few lines of code, but the way you design ergonomic APIs is by obsessing over extra parameters. If you don't obsess over extra parameters, Vulkan happens. Okay, 2 hours in, we have built some BLASs. Let's hope that TLASs will only take an extra half an hour or so and will be good. So the benefit of BLAS per geometry is that the scene is using instancing heavily. We're already using 300 megs of geometry at this point, or of like BLAS data at this point. I worry that if we just pass all of the static scene to the driver as a blob, then it will be, instead of 300, it will be like 700 megs. Having said this, tracing race through a single BLAS is faster than tracing race through a combination of TLAS BLAS. So from the performance perspective, you want one big BLAS, as I understand. But from the memory perspective, you want smaller BLASs because then you can instance them. You could make an argument, for example, that in our scene, maybe half of the geometry is never instanced, and so maybe you could combine that in one BLAS. So there is permutations of this, right, that you could want. For now, this is gonna hopefully work. And then also this will retain an ability to move individual objects. We don't have a notion of static geometry, but again, not super optimal from a ray tracing perspective performance. So it's an interesting thing to experiment with in the future. Like there's different trade-offs here that could make sense. I can trace only against TLAS, but this would mean that the TLAS consists of triangles. I need like a real TLAS anyway, so it doesn't really matter, but that's fine. Yeah, okay, this was already mentioned in chat. Get size doesn't look at data. Yeah, that's sensible. Compacted versions. Yeah, right. That makes sense. The problem is, yeah. Okay. Yeah, right. So that makes sense. So the sizes that I got right now were irrespective of the actual geometry. This is like the worst case. It is possible that the best case is better. The best case would have to take into account the actual values of the geometry. And I guess this is the compaction step that we skipped. But to do the compaction, my understanding is I need to like repeat this process in the sense that I have acceleration structures, and then there's this function called, will copy do that? Or is it like build again? Yeah, this is copy. So I could do a copy with compaction essentially, but let's add this. We don't have ray tracing yet, so we will leave this for the future. And this is the whole memory management aspect that I already talked about. Like right now my scratch buffer usage is the worst case because I'm independently building all of these guys in parallel. And then if I build them sequentially, then I could, for example, compact them one at a time, and the total memory consumption would be lower. There's better ways to organize all of this, like you can batch things in groups and stuff like this. For now, we will ignore compaction, but yeah, it makes sense as to why they are this large, and compaction could significantly reduce this, hopefully. Depending on the implementation, I'm not actually sure. We're using RAD driver, which has its own ray tracing implementation, which I don't know to what extent it supports all of these details. But yeah, thank you. That makes sense. Yeah, so the split makes sense. I don't actually argue, like it makes sense to me that the offsets can be specified separately. It just feels silly that I have to use the addresses and I have to use the offsets at the same time. But really, I think if this thing was optional, things would be a little simpler. Anyway, it's fine. Overall, we have hit no surprises yet, really, right? It's just straightforward, like fill the data, fill the data, fill the data, ask the counts, fill the data, ask the sizes, fill the data. It all was completely fine. So the one thing though is now that I've built the BLASes, I need to build the TLAS. And when we were building the BLASes, we didn't have the geometry, the transform information. It's a little tempting to just build a single BLAS from like instance meshes. The problem is this scene is like, it's fine maybe, right? I think in this scene there's 3 times the number of instance triangles versus the non-instance triangles, so what's the worst that can happen? But imagine running, I'm not actually sure, this will probably work, right? There's no reason why it wouldn't. Let's do this. So this scene has billions of triangles, but only one mesh that's instanced. And right now we have allocated, oh god, we've allocated like 6 megabytes of acceleration structures for this one mesh. But it has like a few thousand triangles. Like that's a lot of memory again. But imagine doing this scene without a TLAS that's instanced, right? That's gonna be like murder. So, which is why I think it could make sense to start with an assumption that instancing is good, and then retract this assumption in the future in specific circumstances. So, because of this, I need to build a TLAS. So, based on what I've seen from the API, TLAS is basically the exact same process, except that instead of triangles, you're filling these instances structures. And then you only get one acceleration structure out of this because we only need one. We could like segment the scene, we could build 5 classes, but then we'd have to trace 5 classes, and that's nonsensical. So what is this array of pointers? Oh, this is like, does the data, yeah, that makes sense, but the question actually is different. The only slight wrinkle there is we'll need to upload our transforms to the GPU memory as like matrices or something. Whoa, this is... Wait, what? Hold on. Wait, motion instance. That's not what I need. Is this just for the NVIDIA's motion extension? How do we build a TLAS then? Hold on. Oh, no, this. Oh, this is geometry instances, and this is... Oof. Okay. What? That is confusing. Okay, anyway. So, we've built BLASs, now we need a TLAS. And when we build a TLAS, we will have the acceleration structure, which is probably a device address. On host, it's the object, but we don't use host builds. So it's a device address, which we will need like a bit, whatever, it's fine. And then a transform matrix. And then some custom stuff that is going to be useful for us in the future, but we currently don't really care about strongly. And we'll need an array of these on the GPU. Let's do this in the same? No. It's tempting to do this in the same function because of the scratch buffer stuff. Actually, no, there's going to be... So this is going to be a little bit inefficient, but let's first do this in a separate function, and then we will come back to this. So we've built BLASs, now we need classes. To get classes to work, we need to specify draw calls instead of whatever we've been doing before. And this guy will just return a single acceleration structure. Acceleration structure. So we give it the device. We don't need the geometry data, but we need the draws. Don't need vertex buffer, index buffer. We'll need the BLASs that we've just built. And then I guess we'll need the BLAS buffer because this is what the reference is for. And then we'll need all of the other stuff. And this thing is going to produce the TLAS, but it will also have to allocate a TLAS buffer for the actual memory. And this is the type of thing that we will eventually need to do every frame if we support movement of objects. And that's a thing that in theory should be way faster than the geometry builds, because like, you know, there's the way there's way less stuff. What is this primitive count and why does it have Oh, maybe it can be null then. Okay. For now, we will just build this ahead of time. So we'll have a TLAS buffer and we'll have a single TLAS. These acronyms are kind of weird, but they kind of roll off the tongue, so I'm kind of digging this. Okay. So draw calls, BLASes that we've built, BLAS buffer, because we'll need like the device address. I don't have offsets anymore. There was... Is there, maybe there's a way to get at the offset? Oh yeah, okay, you can get the device address from, okay. So then we don't need this. So then we don't actually need to pass the buffer there. So we'll remove that. Q, and then properties, and that's that. Remove this. Most of the stuff is going to be sort of necessary, but not quite in the same way, probably. And then we will BLAS buffer, destroy that, destroy that. Doesn't really, the order shouldn't really matter. It's like sort of a little bit more logical to destroy like this, but it should not matter at all. Okay, so let's, and then one moment. I should have probably committed this code, but for now it's fine, I guess. I will commit once we've built both. And then let's convert these to megabytes, I guess, because clearly, clearly all of these sizes are not actually measured in bytes. They're mentioned in megabytes if you're lucky, and then in gigabytes if you're unlucky. And that is that. And this is megabytes, not megabytes. So, and this is going to be the same thing, but for class. So, okay. It's kind of the same thing. Like we need to ask the driver how much data we need, how much bytes we need to allocate them, then we need to create them. It's a little different because we are only creating one structure now. So there should only be one build info. It is nice that the structures are sort of different, but they're sort of similar, and so it is nice that so much code seemingly will be shared, because you can just, you know, like reuse a lot. For now, we'll do fast trace. For classes, I don't know that there's really a difference, so actually this could be fast build as well, or this could just be no flags, but and then we are building it. This is the thing that you might want to do an update if you are updating the classes every frame instead of rebuilding them from scratch. There's no vertex buffers. All of this stuff gets simpler because we only are going to build one structure. So, but we now have more geometries, and the geometry is a BLAS. And then geometry is this guy, so we'll need this. So this is the code that I was writing actually originally, where I had more than one. We don't need all of these offsets because we don't need to sub-allocate. We will not need alignment because we will not. So this is done, or gone rather. This is that. I'm confused about this primitive counts. I'm hopeful that they're not necessary, because it would be weird if they are. If they are, there's no way that they should be. Okay, so oh, and oh no, sorry, hold on, not blast size. So BLAS is the geometries, as in the individual meshes, but then we need to build an object. We'll need to like encode every instance that we have, so every draw into a TLAS. So this is the draw size, and then mesh draws, and then this guy is the guy we need to fill. And the filling is a little different, right? Because instead of triangles, it's now instances. I'm guessing this is not, I don't know. I'd be surprised if this is necessary. Still actually confused by this bit. I see. Okay. It's fine. So this array of pointers thing is like false, and then this data is the thing we need to deal with. So we're gonna fill all of these guys. I mean, it shouldn't matter, presumably. Oh, primitive counts probably refer to like the number of... Interesting. So this probably is actually necessary. Is this really called primitive counts, or is this called some other counts? Yeah, so this is like instance counts. Yeah. So in theory, you can call this API, basically just replace a triangle with like an instance, right? And so you could, for example, build this saying, oh, I have this object, or I have this like geometry that corresponds to this like 1500 instances. We don't have things organized this way, and there's no expectation that instances will be, different instances of the same object will be in the same space, like locally. So it shouldn't matter from the efficiency perspective, I would hope. So, but yeah, we do need this primitive count. Hold on. Is it one geometry then? I guess you could say that there is one geometry. Interesting. Because it's an array, and the count is specified in this primitive counts thing. And one geometry is going to be a little bit easier because there's going to be less. Yeah, so as far as I can tell, what you can do is you can do this. And then you can say this, and then you can say this, geometry, and then we will need to specify the address that points to the array of these structures. we don't have an array of these structures yet, but we will. Okay, so I think this should work because I don't see a reason why it shouldn't work as far as I understand the API. So then our primitive count is like the draw call count. So then we don't need any of that. And then we get the sizes, build on device, build info, there's just one. And then there's just one primitive count, and then it returns us the size info. And then we can just interrogate this size info and ask how much memory do you need? Wait, build scratch size. And then let's comment out all of the rest for now. And then just return a null pointer or something. And then like see what happens. Oh, these are kittens. Yeah, okay. Actually, this is good. So for kittens, there is like 1 million instances, and it's telling us, hey, you need 270 megabytes of TLAS. But very little memory for geometry, right? So now if we work on the bistro scene, it should be reversed. Yeah, it's like a large BLAS because you have a ton of geometry, but a very small class because you have comparatively few instances. And so in the kitten scene, you could imagine that we'd need an insane amount of memory to actually multiply these two together. Not quite multiply, but you know what I mean. So cool. All right, so now we create class buffer from size info acceleration structure size. And we'll still need a scratch buffer. This is where reusing all of these scratch buffers like it's possible, but then you'd need to ask both memory sizes, or you'd need to implement these partial builds that I was talking about, where instead of building everything at once, you build like a few things at a time. Oh, except for here, we need like the total scratch because we are building one. Anyway, it's again a little inefficient, but separate concern. So that is done. Now we need to call build. Similarly to before, oh well, now we need to create it. Similarly to before, we don't need all of this here now because things are a little simpler. Hold on. So acceleration info is inside the class buffer. There's no offset. And then size info build. Yeah, and then it's top level. And then we create it. No. And then this is what we will actually return. And then we destroy the scratch buffer, comment this out for now, and then comment this. And then we have yet to create a buffer with the actual objects, which we will do momentarily. Okay, so I think this is fine, because it will just create it and then bind it and then like destroy it. Okay. So now we need to actually create an array of these structs, and we'll need to create this in GPU memory because except that we don't necessarily have to. I'm gonna create it in host memory because that way I don't have to play weird games with like I should actually sub-allocate scratch, maybe. Where was this? 70 megs, yeah. I should probably put that, but then scratch has to be. This part is like not production friendly. It's not completely terrible, but if you do it once it's fine, but like you don't want to run this code every frame. But we currently are not gonna run this code every frame, so that's fine. So what we need is we need this buffer with instances that we will fill. In fact, we might as well create this like ahead of time here. So this structure will need however many we have rows of. We will need the device address. This is going to be a little weird because like it should be possible. I don't see why not. So I want a host structure basically. And it's probably fine for it to be right combined, so that's fine. And then I will take this structure and feed it to... Oh no, there was this other one. This guy? No. Yeah. Build input this guy. So here, if I can't do this in host memory, then I will adjust, but this is not that much memory and it should probably be fine. I should say we do upload this guy to the, oh, we have this upload buffer helper, but it requires a separate scratch buffer. Let me, because we only do it once, let me just do this in host memory, assuming it even works. And then ideally you do things slightly differently, but it's not too bad. The benefit of doing this is that now we have instances data, which is just a CPU visible pointer to acceleration structure, no geometry, wait, instance. Oof. Instances. And then you can just like write the data there. So this is what we will do. We'll go and I should say we will destroy this buffer. It's kind of single use, I think. My impression is that all of this data should be essentially embedded into the classes and BLASs and whatnot. So we shouldn't need to keep it in memory. Copilot wrote some code that's obviously wrong. So out of abundance of caution, I will mem copy this from a stack one by one, which is probably fine. There's weird problems with write combined memory that are interesting to deal with. So for now, I will just do this. So, okay, so hold on. I will mem copy like this. All right, now let's look at the actual struct. And then let's look at flags just in case we need any. It's actually interesting that I never had to disable. I guess you do this in instance. Yeah, so I'm guessing by default back-facing calling is enabled, which is good, which is what we want. And if you want to disable it, which we will need to do in the future for double-sided geometry, you set this bit. For now, we don't need it, so that's good. All of this stuff we don't need. So this is just calling, basically. So by default, Copilot suggests to disable backface calling. No, we will not do this. So this is all zeros, which is fine. I'm not sure about mask. It will only be hit if the bits are shared. So we do need to set it to all Fs or at least one bit. Otherwise, it's going to be awkward. So then custom index is an index that we will have in the shader, which we might need to reference the actual data of the draw call in the future, not today. So we will save that. And then we need the structure reference, which is the device address. So this is where we will need to whip up this function. It's kind of inefficient. We should probably pre-get these. Let's actually maybe do that. Yeah, so this is just the struct, and it just returns the device address. So for all of the BLASs that we have, let's get the device address. By calling this function, on this structure, and that way we don't have to repeat it for every index that shares them. So then this guy is just draws and then we should assert that this guy is in range. And then the only thing that we need now is the transform. Transform matrix is a 3x4 matrix. And this is where this is the first time, this might be the first time that we've needed a transform matrix for any of our draw calls. So this is this is what we have. We have position, scale, orientation. So we can combine orientation and scale into a 3x3 matrix, and then position is like the fourth row essentially. And then this is where we probably will have bugs with like column row order, which is fine. I forget, there's like a okay, cool, yeah. So we can do form draw orientation. I'm hoping that you can just multiply things with GLM, and then the position is the position, or the third row is the position. Oh, this is an interesting, so this is the offset transform matrix, and then maybe we'll need to transpose, maybe we won't need to transpose. As usual, we will not concern ourselves with such minute details. All right, and then here we just need the get buffer address of the instances buffer. I think we are done with that. So now we just call build. And again, to call build, we need this silly buffer. Silly, not buffer, like the ranges thing. And I guess it's the same, like the primitive count is like the instances. All right, build range. So the primitive count here is the primitive count, which is instances. And then we'll need a pointer to this guy to actually pass into the command. All right, this is silliness, but this is the same silliness that we've already observed. So we only have one build now to do. And then we need like a pointer to pass to this function. It builds it, and we kill the buffers. I think we are done with that. Assuming I didn't misunderstand this primitive thing where you can do one sort of geometry with a bunch of instances. Let's see. Yeah, all right. When we were building the BLAS, or rather when we were allocating the buffer for the BLAS, we should have said this. We should have said that we'll need the GPU address of this thing to pass into TLAS. Oh, I completely forgot to fill that, of course. So after we created the class, wherever the heck this was, here, we should have put it inside the structure. And we of course forgot to fill the scratch data. No, wait. I guess we only need this here. So might as well. So that's done. Okay, so we have built a BLAS and TLAS. And in theory, that is it, in the sense that to just cast ray through this thing, hopefully is going to be very straightforward. But until you try, you don't know. So let me commit this code. This was very straightforward. It just took a bunch of time because I haven't seen the API really, etc. But we have hit like 0 issues, other than the pointers being a little bit redundant. Hey, is it day 24? Yeah. Maybe. We don't know that the builds work, because until you ray trace these, or until you use a ray tracing debugger, which I haven't checked. Like, again, I think the RenderDoc doesn't support this yet, as far as I understand. Oh, we can actually try. We'll try to run this under a RenderDoc now. So like maybe they work. We built one BLAS per the mesh, per mesh, and a single class that aggregates all BLAS instances. This may not be optimal for ray tracing performance, but we kind of have no choice. It's like necessary to support huge instance counts. And again, like there is options down the line. We've talked about compaction briefly. We've talked about maybe you isolate static portions and things that aren't instanced too badly. You have some heuristics where you just pack them in like one big blob. So like there is options. But once we start doing geometry, not geometry, like materials, it's going to be a little bit easier to not pack things this way. So like there's some benefits to what we are doing right now, but it's not unambiguously optimal. Okay. So the final thing that we would need to do is to actually use this data in the shader. And my understanding for what is necessary to happen here is very simple. You pass the class to the shader. You kind of don't see the BLASs because the class like references them. So you just pass the class and then you say, I want to cast array against this thing with this extra extension, and then look at what the array returns. Brief pause. Let's look at chat. I already talked about this at the beginning, but no pipelines and never pipelines, only array query. Array pipelines can go somewhere in some other renderer. Yeah, exactly. Geometry count is one. I assume you can do like geometry count more than one, but like it's kind of doesn't really matter. There may be cases where things like this, I could imagine complex setups where the distinction starts mattering, of course, but in our simple setup, we actually don't care. And yeah, no array pipelines at all. I don't need array pipelines in my life, ever. I may reconsider this in the future, but honestly, I just do not want to work with them at all. So, oh, this should not be here. So the only way to know if this works is to actually try to use it. There is a complication. So I said that I want to make this toggleable. So let's quickly, we are 3 hours in. Yesterday's streams was 4.5 hours. I want to wrap this more quickly than this, but I want to make this toggleable, and this means splitting like a bunch of pipelines. But I'm gonna delete a couple of these anyway in the future. Oh, how do I even make this conditional if I'm not requiring the extension? I can't use spec constants because the SPIR-V is not going to be loadable. So the only way for me to make this conditional actually is... So for now, we are going to cut a corner around the infrastructure, because I don't want to do this today. I have to like, it's not hard, but it's like one more shader and you have to split. It's like annoying. Let's do this like this. We are gonna have like a define here, or maybe let's have a define. Where do we have a define? Here is fine. So we're gonna have a define here, and you'd have to like manually set it to 1 for ray tracing to like work, because for now, and then I'll fix this later at some point, but you need to like split the shaders, and you can split the shaders with specialization constants, I think, if you want these shaders to actually be loadable. So like if you want to work in the mode where there's no ray tracing, which is annoying a little bit, but it's like a necessary evil. And because I want to do some cleanup around how the like remove some of the shaders anyway, I don't want to mess with this right now too much. So for now, there's going to be a define here, and there's not going to be a way to disable or enable ray tracing other than switching this define. So in fact, this ray tracing enabled boolean is like a lie. We do not have this and will not have this. So so my understanding is, oh, but how do you, okay, so now there's a reckoning moment. How do you even do that if, but actually, maybe it will work out. We should have some assertions and stuff. So let's do it like this. Some of the code that we are gonna run right now is gonna be super throwaway, but it's all gonna be behind this if-def, so I feel decent about this. So if ray trace is enabled, then what we need, we will need this extension. Whatever, I guess this guy presumably. Oh no, it's like GL. Whoa. It's definitely not ext ray tracing. Ext ray query. Ray, oh my god. And then once we require the ray query extension, we should have the type corresponding to the exploration structures of this guy. So we will say we really want a uniform bound to like index 7, I suppose, which is the exploration structure, and we'll call it TLAS. So this is what we want to happen. And then we'll enable this for now. And now there's going to be a bunch of problems that we'll hit just from this. Cool. And then we are going to solve these problems one by one. So we have this magical code that parses the SPIR-V blob and extracts like the resource kinds and all of that. And that code will now have to learn about this new thing. Presumably, yeah. So when encountering a uniform of a type exploration structure, we will try to create the descriptor of the relevant kind. Is this not the type? What would it be then? Wait, 0? All right, we are starting to hit problems. Maybe, all right, things might be complicated then, because maybe the encoding is not the one that I thought it would be. This is gonna be a huge hack. But let me just do this for now. I'm a little confused as to why the encoding is different from what I expected. Oh, hey, it's segfaulted, cool. I think I'll need to actually look at the SPIR-V code, because so the way things work is we parse these resource types out of the shaders, and then based on them we create a layout and something in this process, but then we don't specify descriptor. Validation layers are silent, that's fun. It's probably like the draw call failed, or okay, actually this could be a crash in validation layers. Sometimes that happens when. So let me complete this. The SPIR-V parsing change is like bogus, obviously, but I don't want to think about this yet. But I'm not sure how. So I guess my question really is not about this extension, but about this extension. This guy should come with, these nodes are bad. Okay, so let me just grab through this for this type. No. Okay. Oh, this is gonna be annoying. There should be a way to basically pass this object through a binding of descriptors. Oh, unless you get like a view out of this guy. Do you get a view out of this guy? Hold on. So I want this. I mean, you could get the device address. I'm not sure what you are supposed to pass though. Let's see. Oh, yeah. Okay. I need this kind of. It's been a while since I looked at this code. Let me. And I don't actually know, because we are using push descriptors, things are a little bit different. Because this might have to be chained. Oh, and you have to specify. Huh. And I wonder if push descriptors even work with this. Because yeah, we use this like most intricate way maybe to specify descriptors right now. And I'm not 100% confident that it will work. It's interesting that the validation layers are silent. Let me actually see. I should see where the crash is, but wait, what? Oh, it's gonna be weird if I have to. But no, this is not the right structure. But it's extending the thing we don't use. Oh boy, this is gonna be interesting. All right, hold on. Yeah, so this is our descriptor thingy. So the question is, how do acceleration structures interact with descriptor templates? Why does copy paste not work? Again. It will be funny if these are not compatible, period. So this entry specifies the descriptor type. And then let's see. There is a valid descriptor type, but then the question is, what will it read? Let me run this under a debugger and just see where the crash is. It's fortunate that it's a crash on the CPU, not a crash on the GPU, I suppose. Oh, it's a crash on the driver. Nice. So it is going through the path. Yeah, okay. So I mean, we haven't. This is we have like an out of bounds read. Yeah. Okay. Okay. I suspect things are probably working ish. We just should finish the thing we were doing. Maybe. Acceleration structure. Acceleration structure. It is slightly odd that the validation layers are silent, because we are doing like a thing we should not be doing, but there could be reasons for why this happens. We'll find in a bit. So when we do the actual rendering, we have to pass our TLAS, our beautiful TLAS, to the descriptors. So, and we have this weird, like, I'll fix this later, but 1, 2, 3, 4, 5, 6. No, 0, 1, 2, 3, 4, 5. Yeah, okay. So there's some stuff with indexing that I'm gonna fix later, but this path will need like a whole bunch of these. I think this is correct, because this is 6 and then the 7th is TLAS, and this is, no, this is, oh yeah, okay, never mind. 0 based indexing is hard. Okay, so maybe this is correct. I would have expected, oh, the validation errors don't know. But it's interesting they don't parse this information at all. Okay, so, okay, this is fine. The SPIR-V thing we did was a huge hack, but I just need to look at how this information is encoded. So, is there an example in this extension spec that just lets me use this thing? No. I looked briefly. Oh, we also will need a position to cast the ray from. And our fragment shader doesn't have a position. It has a world space normal that it reconstructs, but not a world space position. So let's fix that. Oops. And as usual, we'll fix this duplication at some point. So this is the world space position. And then we will pass that through. And then we need to do the same thing in the mesh shader. And then we need to pass that through to the fragment shader. Okay, so now we have a position, and now we can hopefully trace ray through that in the direction of, in the light direction, which we don't have yet, but, well, we sort of have it here. It's not, we're gonna fix this. If this like works, then we're gonna fix this, and this is gonna be a great stream. If this explodes right now, then this is going to be a bad stream. Because again, right now, we just don't even know if the data that we have filled is remotely accurate. Like, the structures are built, so it's unlikely that something is catastrophically wrong, but things could be... we could be in different states of bad right now, and it's hard to tell. So the way this extension works is once you bind the structure to the shader. Oh yeah, okay, here's the example. Great, we are gonna steal this as is. So you have this object ray query and you initialize it. When you have, we only need the first hit ray, which means it stops when it hits the first object. In more complicated cases, you may want to hit an object and then look at an object and then decide what to do after. And we'll do this like in the future, but for now we don't need to. So for now this is okay. All of the data is in the world space, so theoretically we just pass position. T-min, T-max, I guess is 0 infinity or something. Let's just cast a finite ray, and then direction is going to be sun direction. And then you call proceed. This like does nothing useful, just fills the bits. And then this you call once for every like next step that the ray takes, but for us there's only one step. And then this is what will tell you if the hit is oh, this is saying the ray hit nothing. So if the ray hit nothing, we're good. But if the ray hits something, then we have to cancel the end.l. So let's cancel it for good for now. And then, well, let's do it like this. I don't know. Let's run it. Ray query ext. Oh, huh? Hello. What do you mean not? What? Wait. Didn't we? What? Hold on. Huh? Array query ext undeclared identifier. But we just requested the extension. How does that work? What? Huh? That is interesting. No. Yeah, it's just a type. Doesn't have to be uniform, right? Like it's declared with no storage qualifiers, either in the global scope or within the function scope. Huh? Wait, what? That is surprising. We're clearly not enabling something. Let's see if the chat just says. So this is GLSlang. Let me go to GLSlang repository and just search for ray query ext and then see what comes out, because this is surprising. Like there's only one extension. So I don't understand why it would fail. Yeah, like this is, well, this is an rgen, so let's look at the fragment shader. Oh, they declared this in global scope? Huh? I mean, I don't really care, but it seemed as if you can declare it in function scope. No. It's interesting, it behaves as if the extension is disabled. Oh, do I have to enable it instead of requiring it? That makes no sense. No, 49. Wait. So it enables ray query and then just declares it. And this is actually our error. We don't really need anything else. We can just comment out this stuff. And the... It's interesting that the error is a little different based on where I specify it. Here it says undeclared identifier. So basically it looks as if, is it possible that my GL slang build, oh no, GLSL, GL slang validator. So, okay, hold on. Do I have two? Well, it's the same binary, okay. So I wonder if this version of the binary is somehow like old. No, but it didn't complain on the extension though. So it ostensibly should. All right, let me see. But yeah, there's nothing weird about this type. That is weird. Let me see. So I do wonder if the binary is somehow weird. Ray query. So we require it here, and it's interesting. Like the declaration structure was fine. It's just a ray query. I don't understand this at all. I mean, I can like remove the if-def, but that's not gonna help, presumably. Unless there's some issue with preprocessing. No. This is just broken. Okay, so maybe I target 1.3, but you shouldn't have to specify the extensions on the command line. So let me try to... Surely. Thank you. Whoa! We have shadows. They're wrong. Kinda. They're wrong, but we'll okay. Hold on. This is interesting, but okay. What is for 60, 50? This is a little wild, but okay, yeah. The errors are interesting in this case, right? Because you would think you can't require an extension maybe until version 4.50. Maybe it's like ray queries. No. So yeah, it should have been an error, I guess. But okay, all right. Thank you for the suggestion, because that was the problem. That's a weird corner case. So we have ray tracing almost working. We are gonna make it fully work, and that'll be the stream. So why do I say that it's almost working? Well, things are slow. Minor details. We are running at 7.7 milliseconds GPU. We were running at 0.8 before. But I said last time that once we enable ray tracing, all of our performance considerations will change, and that indeed did happen. For example, this may, it's funny, we're just casting one ray. It may mean that things will change once we fix the visuals, perhaps, because clearly things are a little broken right now. But this kind of looks like transposed rotation matrices, actually, because this sort of looks like transposed rotation matrices to me. So let's fix that first. But yeah, performance is not great. This is one ray. Well, this is 4K though, so there's that, but it is 1 ray per pixel. And this may mean that we'll have to switch our approach and then actually do deferred and then, like, you know, denoising and all of that stuff, so that we can, we clearly can't afford 1 ray per pixel. We can, but 7 milliseconds is too much. We are running with validation enabled, but it should not inject any GPU code, I wouldn't think. Anyway, okay, hold on. So where do we do that? We do that here. So the theory would be that we need to transpose the matrix because the column row thing is flipped. So this is correct, I think. Obviously, we have biasing issues, which we will have to have a small offset for. But I think things are correct, maybe. Now, the thing is, we aren't using the correct sun direction, but we'll fix this momentarily. So I assume we can just do this. Let's say we could use short arrays. I'm not sure if it's going to help our performance problems. Okay. That looks very correct to me. This is, well, so obviously we are not doing the transparency. So you see, for example, the shadows like on this wall. And this is not how they are supposed to look, because we are casting a ray and the ray hits the geometry that is supposed to have alpha tested texture on it, but we aren't doing alpha testing and ray tracing, so it doesn't work. 24 milliseconds, oh my god. I guess the ray would often hit whatever it would often hit. Whoa, this is slow. This is not even 60 FPS. I know it's a 4K resolution, but this is the time. So when you use Wayland, it uses the full screen pixel resolution. When you use X, it uses, at least GLFW, uses the resolution, like scaled, inversely scaled by the DPI scale, which I have set to 1.5, because, you know, so now we are running at 14 milliseconds per frame, but that's because we are rendering at not 4K, at sub 4K resolution, and then things are upscaled back. All right. But then you see visible, no, wait, actually, hold on. Then you see visible stair stepping on geometry. So yeah, this is all saying we either need to do, what's it called, variable rate trading, or we need to use, it's either variable rate trading or the like separate, you know, dump the depth buffer with G buffer stuff. I'm not gonna attempt variable rate shading because it's the stream has been long, but it actually might not be very hard to do variable rate shading with a very, very simple setup where there's just a way to tell it shade like every second by second pixel, and the shadows will not look as nice, but all right. So oh, and let me see just what happens if I like set this to 0. And again, the only reason why, since the extension isn't required by this application right now, yeah, and then we run at 1 millisecond. It's actually small. Right now, the GPU is not being clocked fully because 1 millisecond is not enough time for it to like be kind of overloaded. But obviously, it used to run at like 0.80 something, 85 at full clocks. But when we have ray tracing, I'm assuming it runs at full clocks because I'm not sure what else it would be doing for 24 milliseconds. So yeah, not super fast. For now, let me set it to 0, and then I'll just have to like remember to enable it manually. Oh, there's SPIR-V hack. Let's fix the SPIR-V hack because I don't like this. So there was some weird issue with, I guess, how these are declared in SPIR-V. So wait, let me, so this, and then we need to fix the sun direction, and then that's it. So when we parse the SPIR-V blob, we extract the types that we are using for the individual uniforms. And when we were parsing the type for everything else, it's just a value. And for this guy, it's like weird. So let me see. So we have this TLAS that is reflected somewhere. So it is descriptor set 0, binding 7. And then someplace else, there should be an actual object that points to that. It would be a little faster if let me dump this. And then let's just search for acceleration structure. I've written this code years ago, so I don't recall how this works. Let's see. So we have a uniform statement that has a type ID that goes into so what we are looking for actually is op uniform, perhaps? No, probably not. Okay. Let's look at the other stuff that does work. I really don't remember this. So I guess we should have like a sampled image somewhere here. 41. Oh no, this is the array. No. What else are we using in this shader? We are using this buffer. So, and the buffer should be of type struct. So we should have somewhere here op type struct. Yeah, so this is the mesh draw. So this is the type struct. And it's referenced by the array. Yeah, so this is the thing that we want to parse, except there's an equivalent for this that's like an acceleration structure. Oh, is it just a case? Hold on. No. Is there somewhere else where we extract this, which we just don't do? No. Interesting. Okay. All right, one moment. I unfortunately don't remember very much about this code. So there is this pointer to a uniform constant, and then there's a variable with this type, which is a uniform constant. And then this is what is decorated with the descriptor set. When we parse pointer types, we save the type ID and the storage class. Wait. So when we parse this guy, we parse uniform constant and this, but this is a reference. So maybe this is the problem, where when we have op type pointer, it saves like the wrong type ID. it would have uniform constant, and then this would be the link to the right type. Is it? Because yeah, there's no op type. Oh no, there is op type. Wasn't it? It is weird that it was 0. I guess I'll need to like actually debug this. Alright, fine. You know what? This is silly. I'm just gonna fix it later, like off stream or whatever. It's gonna. I'm just like not extracting the. Oh my god! Stop inserting U's everywhere. I'm just not like extracting the right information from SPIR-V for this specific case because the layout is like not expected. It doesn't really matter. The thing I wanted to do instead is to commit this code with this hack, whatever, I'll fix it later. Everything else is not a hack, except that we can't vary the support for this at runtime, but it requires some cleanup that I don't want to do yet. So ray tracing works, and it's slow. This is the case where maybe one BLAS would have been faster. I seem to recall that on AMD there is no acceleration for the PVH traversal, which might penalize this more than it usually does. I'm not sure, but regardless, like, so yeah, this is slow, but slow is good. We can solve this problem at a different point in time. Ray query to cast a shadow ray per pixel. So performance is not great, and also the lack of support for transparent objects or alpha cut objects is not great, but it's all like, you know, some other time. Okay, and we also can't toggle this at runtime quite yet. So use define in mesh fragile cell to enable manually. And I switched it back, right? So I have to switch it back to actually commit this. All right, so one last thing is I want to fix the sun direction because the scene has a sun direction that I have carefully picked out in Blender. And it would be nice to like use it, I guess. So we will have a sun direction that, yeah, like by default is some arbitrary value, but then we will allow the GLTF scene to override it. I should say this was infinitely less stressful than the stream yesterday, because the stream yesterday I just felt like I'm fighting these layers and layers and layers of APIs for like a solid 2 hours, and this time everything was intuitive. The only two things are device address stuff, which I understand, and actually, yeah, like this is probably a good idea, but like the only other thing was this extra pointer business that just feels artificial, but like none of this is major. So everything was actually super smooth. I think I looked at this before. So there's a light with a direction, and again, God knows which way the columns or the rows of the matrices are. I think this is correct, maybe, but maybe it's minus. I think this might be the right thing. I forget, because I think it's like -z. We'll find out. And then I have this struct globals that has a bunch of stuff that I'm gonna clean up in the future, but it should have direction, and then here, and then globals projection, globals sun direction. So that's that. Right, and then we actually enable ray tracing, and then instead of the hacked up thingy, we use the global thingy. I don't think we use, we obviously need, let me steal this from somewhere. That is a weird order. Clear it isn't, right? Maybe this is, maybe not minus. I looked into this, but I really don't recall. Okay, yeah, this is right. That is exactly, so now we can open Blender and then load the same scene and then compare them. Blender's scene will look nicer because they have like features and, you know, they have like a path-traced render as far as I understand, or maybe not fully path-traced, I'm not sure, but it's also taking a while to load textures, like a while. Like it should have been done already a while. Hello. Oh my god, this is slow. Is it struggling because I have a slightly intensive GPU app running? I don't. Okay, finally. And then actually I need this button, I guess. Okay. And then we can, again, start our application, which starts faster in Blender and stuff. So now we can compare and contrast. The framing is wrong because I think if I think I should press like F. Oh my god, where's the camera? Whoa, Blender is like seriously unresponsive when I have our code running. Okay, wait, no. All right. Hold on. I thought it's like F4 or F5 or something. No, I don't want to render it. I just want to... Blender UI breaks occasionally for me in this weird way. I don't recall if it's just... I probably entered some weird mode. Oh my god, okay. I think we are back. Okay. I thought it's like F4 or something. All right. Camera. All right. But now it is not framed correctly. Oh yeah, okay, it is F4, but the framing is off. Okay, so I think this is the correct framing. And then we can open our scene again. I haven't even checked if these, oh no, yeah, okay, this definitely did work. And then we open it at full screen so that it's the same aspect ratio. All right, so this is clearly the correct rendering, except that the Blender scene looks a little nicer, you know. We probably, point one was probably a bad call because we already have ambient. And so the scene is kind of washed out. There's all sorts of sRGB issues, etc. But the sun direction is correct. All of the shadows that you see, they are the same. Of course, our shadow is sharp and Blender's shadow is soft. But clearly on this GPU, the first order problem is not to get nicer shadows. The first order problem is to get faster shadows. But we are not going to do that today. Oh, the one thing I should mention is like we are using the highest level of detail right now to cast shadows. This can be a problem for multiple reasons. One is it can generate false occlusion. And then the other one is it's just going to be slower. But we are definitely not gonna attempt this because, you know, it's almost 4 hours and I would like to end the stream at the 4 hour mark, not at the 15 hour mark. But this is great. We have achieved everything that we have set out to do. Thank you people who were watching, and especially thank you Christoph, who helped a few times with some stuff that we had which had issues. Yeah, so the colors don't match. Like there's many reasons for why the colors don't match. I don't think the textures like are a problem necessarily, but I need to double check but there's all sorts of problems. We aren't doing gamma correct lighting. We do all sorts of this weird like shading. I don't know. I just put like a 0.1 ambient yesterday on stream, I think. Now I have this extra 0.1 in shadow. It's all bad. Like, you know, there's an opportunity for improving a lot. We are ignoring colors on materials and we're ignoring colors on the sun. So if the sun in Blender has like a yellowish tint or whatever, we are not using that at all, etc. So there's all sorts of reasons for why the colors will be off. The important thing is the shadow direction is correct. And then, of course, as you see, because we don't do alpha testing now on these objects with cars, the shadows are like really weird. So there's a lot of work to be done for this scene to look nicer. And then also there's a lot of work to be done for the scene to render faster, because 20 something milliseconds for a 4K scene is a little bit too much. Let me commit this code. And now render shadows at an angle matched with Blender. Which is not saying a whole lot, but hey, it works. Oh, the suggestion for 460 was from Amar. Thank you, Amar. Yeah, this was correct. Target env is 1.3. I don't have a depth prepass, but I do have occlusion culling. Having said this, I don't know what the effectiveness on this is. But yeah, it is possible that we are casting more rays than necessary just because we have some amount of overdraw. We can check this in RenderDoc. In fact, maybe we should see what the what's like the we can check the overdraw even without ray tracing. So yeah, don't take the stream as, oh, we have concluded that on AMD hardware ray tracing is unusable. Obviously, there's like a lot of inefficiencies that we have that we could correct. And there's like, I'm sure it can be way faster. I also suspect that doing array per pixel at 4K isn't what this GPU would really like. So I suspect there is both things. But let's just, so RenderDoc has somewhere support for, there's definitely some pixels where there is, but anyway, we definitely have some issues with overdraw. I just don't know how bad they are. Oh, there's only quad overdraw. Is there really only quad overdraw? Because quad overdraw is not what I care about at all. But okay. This is annoying because this is not what I want. Well, I guess it's kind of what I want. I guess it's kind of what I want. Sort of. I'm not, I need to think about this. But yeah, there's definitely some, obviously there is these hot areas, which, so this is why I'm not like sure, but you'd have, yeah. This is an interesting question as to whether a ray query from the fragment shader is even practical, because there's some fundamental issues here that are difficult to fix without deferred. We're like reasonably set up to defer those, so if we need to do deferred, we absolutely can. There's not like an issue, and we can even do deferred with this buffer so that we don't have to spend like a bunch of memory on the G buffer. So there's like many ways for us to rework things in the future for them to be faster. But yeah, there's definitely some overhead, which is very much not zero, from different types of overdraw in the scene. Problem for another day. Yeah. So yeah, I'm curious what would actually happen. Oh, yeah, so I think actually what happens right now is that RenderDoc, I would assume, doesn't support ray tracing resources yet. So I would assume that RenderDoc hides the support for ray queries and stuff from the app. And then because we don't use this in the fragment shader, then it's fine because it just works. But I don't know, I haven't looked into the level of support that RenderDoc has. Anyway, that is kind of it. So I don't know if people have more questions, but this was productive. The one thing I can try to do, which is actually going to be interesting, the last thing that I will try to do is this. So let's go back to Wayland to see the problem, to tackle the problem in its full severity. So what I can do is I can capture an RGB trace, and then I assume the RGB trace will still be perfectly functional with ray tracing. And then we will do this at this smaller resolution to have it be less like... we can't. Things crash. Why do things crash? Interesting. So I guess we can't enable... Whoa. The device creation crashes. So this is a bug in RAD, clearly, because it can't be a bug in our code. We are just creating the device. But I do wonder, I have a very recent Mesa build. I forget where it is. It's like every time. CMD, like the Bradion, something. 1 second. Yeah, so this guy is what we need. And then if we set wiki driver files to this JSON, then it will use the latest. We kill GDB from this. It actually might crash the stream now. This is dangerous to do. Oh no, okay, it works. I didn't type. I don't recall. It's like wiki trace, maybe just frame. Okay, so there was a bug in the whatever version of Mesa ships with my Ubuntu that I guess was fixed in latest. Oh, the performance is faster. Interesting. So I guess the GPU was underclocked during our earlier test. It's still slow, but it's faster. I don't know if the stream will crash now though. Oh no, okay, it's fine. All right, so let's look at Radeon. AMD also has a specifically ray tracing targeted like profiling tool, but we are not going to use that for sure. It's interesting how slow even the second pass is. So this is the main geometry pass, and then there is like some geometry that's not occluded, or that is like the second pass of occlusion, of the two-pass occlusion renderer, that's like basically empty. But this is the alpha tested stuff, and it's pretty slow. You do kind of want a deferred setup for maximum efficiency in cases like this. There's decals on buildings here, and we are effectively shading pixels of these decals, or not shading, but like ray tracing pixels of these decals twice. Having said this, you know, like let's say we start doing reflections and the wall under a decal is not reflective, but the decal over it is like 50% reflective. How do you do reflection for this? Kind of, sort of want to do twice. I don't know. It's a brand new world. But yeah, so what do we have here? Is there a way to see like ray tracing activity, or I guess that's all in compute or in the we should be able to see the fragment shader, and then somewhere here there's ray tracing stuff supposedly. Clearly is, did I have instruction tracing on? So the instruction timing view should have wait, this is not the fragment shader. Where's the fragment shader? No, this was the fragment shader. Okay. So for example, these instructions are hit a whole lot. Oh yeah, and so you see, for example, the image BVH64 intersect ray function instruction that is hit like a whole lot in this fragment, in the shader fragment. And then there's some other stuff here. Fully studying this is like a full separate stream, obviously. It's interesting that this is called BVH64 intersect ray. Maybe this is ray bounding box, and the bounding box is like backed in some way. And then there's some other stuff here. This looks like the BVH traversal because it's like a bunch of conditionals, and like is this greater than this, is this less than this, and branches and stuff like this. So this kind of looks to me like the actual traversal loop. And then all of the shifts. This is how you would usually expect it to look like. It's interesting that then there's a bunch of math with reciprocals and stuff. Is this the... No, this is not the prologue. The prologue is like super early. Interesting. So this is like the ray preparation probably, like somewhere here. And then it like fills flags and whatnot. This is kind of corresponding to the ray query setup. But yeah, all of this looks like the BVH traversal, and you can Google like MDI is public. You can Google what image BVH64 intersect ray stands for. I would make a bold guess as to this being like a ray versus a triangle packed into like the BVH64 format. And then I would guess that the rest of this code is the bounding box intersection and the BVH traversal, but I'm not sure. Image BVH64 intersect ray. We are using RDNA 3, but I guess the instructions are the same. Oh yeah, okay. I am wrong, I guess. Oh, this does both. Oh, interesting. It's suspicious because there's like a ton of floating point math around these instructions. Because it says performs the intersection test and returns the point. And this sorts and returns the child pointers and hit status. So this says that like, and this is just a 64-bit address. Only one ray triangle intersection test, really? Okay, that's not how I thought things would work, but okay. It's one per thread, but still. I am surprised at this, because this says as if, oh, the instruction just does everything, but then if I look at the actual ISA, then there is so much math around it, and so much branching, more than just should we go in or not, but like, it's as if, like, what does this do, for example? Because, yeah, sure, we intersected the ray. I guess these are, sure, they're less common, but still, like, this, the RCP here, which you wouldn't even need. Yeah. So, I don't know. I haven't looked into this closely. I am a little surprised because one possibility is that the RAD driver actually... Let's do one last thing. I'm just very curious. We will not have as easy of an RDP access with this, but I'm just very curious. So one last thing, one last experiment. Hopefully nothing crashes and burns. And then I'll look in chat and then we'll end this. So as I was saying in the beginning, next stream, sometime in December, I'm not sure when, we'll see. But this was very productive because we achieved exactly what the plan was. So yeah, like 11 milliseconds. Let me disable vsync just in case, but I don't think that should matter. Yeah, basically 11 milliseconds per frame. This is like a smaller window size, right? Way faster without ray tracing. So I have a driver that is the official AMD driver that I can just live install because it's just a user mode driver, and it will replace the RAD driver that we have been using automatically. And I'm just curious what will happen. Yeah. So RAD driver has work to do. This GPU, this is still not amazing levels of performance, but this is almost double the speed of the RAD driver on this scene. Why that is the case, I can't tell you because I don't know. You should be able to do an RGB trace capture from the official driver, but I just don't remember. I don't know how to do this because I've been relying on the MESA's support for this. So I don't know how to show the same like instruction trace for this. I know how to do this on Windows, but that's like a machine reboot and it's been too much time. But the official driver is way faster with ray tracing. Here we can render at 4K at 60 FPS with a little bit of headroom. Again, is it the ultimate peak performance? No, I was hoping to get slightly more than one ray per pixel, but maybe at 4K is just unrealistic and you just should go lower. And then there's all of the overdraw issues and stuff like this, so like it can be faster. But it looks like from this that RAD is competitive on geometry, on rasterization. In fact, it's faster a little bit by like 5%, I think, on this level than the official AMD driver, but it's substantially slower, looks like, with ray tracing, at least with ray queries. So that is not going to be my problem. Oh, did I check what the performance is? I did not. Let's just double check what the performance is on the latest Mesa, but I think it was it similar? I think it was similar. Let's see. Just to get a fair baseline, latest to latest. Yeah, it's the same. So it's like 11 milliseconds, give or take, on RAD, and like 6.8 or whatever it was. So it's not quite half the speed, but it's like close, too close. Okay. Anyway, we will leave this here. Maybe I'll switch to the official AMD drivers for a bit then, because it looks like on ray tracing they have more reasonable numbers. And then we will meet again, hopefully, in December. Let me see if I'm missing anything else from chat. I am not missing anything else from chat. So that is it. It's been slightly over 4 hours, which is a good point to end the stream. Thank you everyone for coming. And whenever, as usual, announcements for the next stream, whatever is your social, whatever is your Twitter replacement of choice these days, including Twitter, you know, like it will show up there. All right. Thank you. And bye.